For 70 years we got it wrong. The Milky Way is not 100,000 light-years wide. It is twice that size, and maybe even more. We have been living inside a galaxy double the scale. Double the scale we taught in every classroom, double the scale charted in every single textbook, double the scale calculated in every scientific paper. New technology has just revealed the truth, and it changes everything. How we measure the universe, and when Andromeda hits us, and whether or not we are truly alone in the cosmos. This is the story of the biggest correction in modern astronomy. Open your old astronomy textbook and find the diagram of the Milky Way galaxy. That elegant spiral with neat measurements is wrong. It shows 100,000 light-years across. It is completely and utterly wrong, not just a little off. Not outdated by a few percentage points, but wrong by a factor of 2. Every poster in every classroom, every documentary animation, every Wikipedia diagram that you have ever trusted, they all show a galaxy that is half of its actual size. Scientists have known that something was off for many years, but the data that they had came in fragments and hints, anomalies that did not fit the established models, stars that were moving too fast at the edges of the galaxy, satellite galaxies that were orbiting much too far out, mass calculations that never seemed to balance out correctly. Then the new measurements started pouring in from new telescopes, Gaia spacecraft data, and James Webb observations. Radio telescope surveys mapping hydrogen clouds at the fringes. Each new instrument revealed the very same shocking pattern. The Milky Way extends far beyond where we thought it ended. The problem is not that the astronomers were careless. The problem is that we have been trying to measure our galaxy from inside it. Imagine standing in the middle of New York City and then trying to draw its exact boundaries. You cannot see the edges of the city from your position. You cannot step outside for a better perspective. You are completely surrounded by buildings, lights, and noise. That is us floating in one spiral arm of the galaxy, 26,000 light-years from the galactic center. We are drowning in a sea of stars and cosmic dust. For many decades, scientists used a very simple method. They looked at the brightest stars they could see in every direction. Where the number of stars thinned out, they drew a line. That line became the official edge of the galaxy. 100,000 light-years case closed for them. Except it was never really that simple at all. The galaxy does not have a sharp edge like a dinner plate. It just fades away gradually into the darkness of space. Stars are scattered outward in thin streams and clouds. Dark matter, which is invisible and massive, extends even farther. The old measurements only tracked the bright parts of the galaxy. They only tracked the obvious and easy-to-see parts. They missed the enormous halo of material that is wrapping around everything. Here is what changed everything for the astronomers. Scientists started to track what are known as stellar streams. These are rivers of stars that were torn from smaller galaxies, galaxies that the Milky Way devoured millions of years ago. The streams are orbiting through space like cosmic fossils, and their paths are revealing the true gravitational pull of our galaxy. When researchers mapped these streams, they found them circling far out, far beyond the supposed edge of the galaxy. 200,000 light-years out, and maybe even more. The Milky Way is a giant, and we have been measuring a shadow. This discovery does not just change the numbers in a textbook. It is rewriting how we understand the structure of our galaxy. It is shifting the timeline of when Andromeda will collide with us. It is doubling the volume of space we need to search for life. Every calculation that was built on the old size now crumbles. But the most disturbing part of this is the implication. If we got our own galaxy this wrong for so long, what else have we miscalculated in the universe? How many other galaxies are twice as large as we think? Picture this scenario for a moment to understand. You are blindfolded standing somewhere in the vast Sahara Desert. Your job is to measure the entire extent of the desert. You cannot remove the blindfold that is covering your eyes. You cannot use a GPS device to help you navigate. You can only feel the sand beneath your feet and listen to the wind. How accurately do you think you could map the desert? That is the challenge that astronomers are facing. They are facing it when they are measuring the Milky Way. We are sitting on a rock that is orbiting an average star. It is in an outer spiral arm of our home galaxy. Thick dust clouds are blocking our view in almost every direction. The galactic center is hidden behind thick walls of gas and debris. We can see maybe 10% of the galaxy with optical telescopes. The rest of it is hiding in the infrared and radio waves. For comparison, measuring the Andromeda galaxy is easy. It is sitting 2.5 million light-years away from us. We can see the whole thing at once from edge to edge. We can photograph it, map its spiral arms, and count its star clusters. Measuring our own galaxy is like trying to photograph your own face. Doing so without a mirror while you are standing inside a thick fog bank. Early astronomers had no other choice but to do this. They measured what they could see with their instruments. They tracked the Cepheid variable stars which pulse at predictable rates. They calculated the distances to the globular clusters. These are ancient balls of stars that are orbiting the galactic core. They built up a map of the galaxy piece by piece. It was like assembling a giant puzzle while blindfolded. The breakthrough came when scientists realized they could use motion. They could use motion instead of just the light from the stars. Everything in the galaxy is orbiting around the center. The stars, the gas clouds, and the entire star clusters, they are all moving at specific speeds based on the mass. The mass that is pulling them in with its gravity. If you measure the speed, you can calculate the mass, and then you can estimate the size of the galaxy. But here is where things started to get very strange. The speeds of the stars did not match the expectations. The stars at the very edge of the galaxy were moving way too fast. According to the visible mass, they should be flying off into space. Something invisible was holding them in their orbits. This something was dark matter, an enormous halo of it. It is wrapping around the entire galaxy like a gravitational cocoon. This is where all of the old measurements had failed. They had only counted what they could actually see. The visible stars, the glowing gas, and the bright nebulas. They had ignored all of the invisible mass of the dark matter, the dark scaffolding that is holding everything together. That was the fundamental mistake that they had made. Modern telescopes have now changed the entire game. The Gaia spacecraft is tracking the precise movement of over 1 billion stars. Radio telescopes are mapping the hydrogen gas that is extending into the outer halo. Infrared instruments are able to see through the dust clouds. Each of these new technologies is revealing a different layer of the galaxy. Researchers also started using the satellite galaxies as test masses. The Milky Way has dozens of smaller galaxies that are orbiting it, the Large Magellanic Cloud and the Small Magellanic Cloud, the Sagittarius, Dwarf Galaxy, and many others. These galaxies are orbiting based on our total mass, the visible and the invisible mass combined together. If you track their paths, you can map the true gravitational field. When the scientists combined all of this new data, the answer that they found was completely shocking. The Milky Way is not the medium-sized spiral galaxy we imagined. It is a heavyweight, a true galactic giant in our universe. It is double the width and it is triple the mass. And if measuring our own galaxy from the inside was this hard, what happens when we try to measure even farther out? Stellar streams sound exotic, but they are actually galactic crime scenes. They are the evidence of past violence that is frozen in time. Millions of years ago, small galaxies wandered too close to the Milky Way. Our immense gravity grabbed them and pulled them apart. It stretched them out like a piece of cosmic taffy. Their stars did not just vanish into thin air. They were scattered into long rivers of brilliant light. They are now circling our galaxy in very thin streams. Some of these streams are wider than the Earth's entire orbit. Others contain thousands of stars that are moving in perfect formation. We never paid much attention to them before this. They seemed like just a part of the background noise. They were faint, distant, and seemingly irrelevant. But they are the most honest rulers that we have for measuring the galaxy. Here is the reason why they matter so much to us. Stellar streams are following orbital paths that are determined by gravity. Every single star in the stream is moving based on the total mass that is pulling on it from our galaxy. If you measure the path of the stream, you can measure the gravitational field. There is no guesswork involved, and there are no assumptions. It is just pure, unadulterated physics in action. The Sagittarius stream is the most famous of these streams. It is wrapping around the entire Milky Way galaxy multiple times. It is like a beautiful ribbon on a cosmic present. Scientists have traced this stream all across the night sky. They realized that it extended far beyond the old galactic boundary. The stream just keeps on going and going and going. This means that the Milky Way's gravity also keeps on going. Then came the discovery of the GD1 stream in the data. This is a very thin river of stars in the outer halo. Researchers mapped its curve and found something impossible. The stream was bent in ways that required far more mass than the visible galaxy contained. Either our physics was broken, or we were missing something massive. Dark matter is always the answer to these kinds of problems. The streams were revealing it like invisible ink under ultraviolet light. The gravitational pull that was shaping these stellar rivers was coming from it, material that we cannot see, and that extends twice as far as the visible stars. But what comes next in this story is even stranger. Scientists have found streams that are orbiting at very great distances. Distances that we thought were in intergalactic space, the empty voids that are located between the galaxies. Except that these regions were not empty at all. These streams proved that the Milky Way's influence reaches farther than anyone had ever imagined it could. Our galaxy does not just stop at its visible edge. It keeps on pulling, keeps on claiming territory, and keeps on exerting control. The Orphan Stream is a particularly haunting example. It is orbiting so far out that for years scientists debated its origin. They debated whether it even belonged to the Milky Way at all, or if it belonged to some other, more distant galaxy. New measurements have now confirmed its true nature. The stream is ours, which means the Milky Way extends at least that far. Each new discovery of a stellar stream added to the galactic radius, 5,000 light-years here and 10,000 light-years there. The numbers just kept on climbing higher and higher. 120,000 light-years, then 150,000, and then 180,000 light-years across. Stellar streams gave the astronomers something that they desperately needed. They gave them the ground truth about the size of our galaxy. You can debate where the edge of the visible disk sits. You can argue about where the darkness becomes intergalactic space. But you cannot argue with a stream of stars that are orbiting in formation. Their path is the truth about the extent of our galaxy. And the truth just kept pushing the boundary outward, farther than was comfortable and farther than was explainable with old models. 200,000 light-years, the streams said so, the math said so, and the observations also said so. The question was no longer how big the Milky Way is. The question became, how did we miss this for so long? You are staring at the Milky Way galaxy right now, or at least you think that you are staring at it. What you are actually seeing is just the skeleton, the bones. You are only seeing the bright and easy-to-see parts. 90% of our entire galaxy is completely invisible. Dark matter is not just a theory anymore, it is a confirmed fact. It has been measured, it has been mapped, and it is real. We cannot see it directly with our telescopes, but we can see its effects everywhere that we look. The stars in our galaxy are orbiting much too fast. The galaxies are spinning without flying apart into space. The light from distant objects is being bent around invisible mass. The evidence for the existence of dark matter is overwhelming. In the Milky Way, dark matter does not just add extra weight, It is what builds the entire structure of the galaxy. Imagine a massive skyscraper where you can only see the windows. You cannot see the steel frame that is holding them all up. That is what our galaxy is like in reality. The stars are just the windows and the dark matter is the frame. Scientists have estimated that dark matter outweighs the visible matter. It outweighs it by a ratio of about 10-1. For every single star that you can see in the night sky, there is 10 times more invisible mass that is nearby. This material forms a massive halo around our galaxy. It is spherical diffuse and it is stretching far beyond the visible disk. The old measurements of our galaxy had ignored this vast halo. They had focused on the bright spiral arms and the glowing core, the obvious features that are easy to observe. The galaxy appeared to be 100,000 light-years across. This is because that is where the visible stars thinned out. But the dark matter just keeps on going and going. It extends twice as far out and maybe even more. Think of it as being like a massive iceberg in the ocean. You can only see the tip of it that is above the water. That is the visible part of our galaxy, the stars and the gas. Below the surface, hidden from our sight, sits a mountain of ice. A mountain of ice that is 10 times larger than the tip. That is the dark matter halo of our galaxy. The true size of the galaxy includes both of these parts. Researchers are mapping this halo using gravitational lensing. When the light from a distant galaxy passes near the Milky Way, our dark matter bends that light just a little bit. If you measure the bending, you can calculate the mass. The results of these measurements have been shocking. Our dark matter halo extends out to nearly 400,000 light-years. This is when you count all of the faint outer regions. But here is the twist in this particular story. Scientists are still debating where to draw the line. When does the Milky Way actually end and intergalactic space begin? Is it where the dark matter density drops to half or a quarter? There is no official edge, just a gradual fading into nothing. For practical purposes, astronomers use a measurement called the virial radius. This marks the point where material is gravitationally bound to the galaxy. Inside of this radius, everything is orbiting together. Outside of this radius, space is truly empty. For the Milky Way, the virial radius is around 250,000 light-years. This is double the old estimate of the galaxy's size. All of this is because of the invisible mass of dark matter. This changes how we think about the structure of galaxies. Galaxies are not just islands of stars floating in empty space. They are enormous halos of dark matter with stars sprinkled in the center. The visible part is just the decoration on top. The invisible part is the real substance of the galaxy. And if our own galaxy has this much hidden mass, every other galaxy in the universe probably does too. The entire universe just got a whole lot heavier. The Milky Way is not alone in the vastness of space. Dozens of smaller galaxies are orbiting around us. They are like moons that are orbiting around a giant planet. We call them the satellite galaxies of the Milky Way. And they have just rewritten our own cosmic address. The Large Magellanic Cloud is the biggest of these satellites. It is visible from the southern hemisphere as a cloudy smudge. It contains about 30 billion individual stars in total. The Small Magellanic Cloud is sitting nearby with 7 billion more. Then there are the even smaller dwarf galaxies to consider. The Sagittarius Dwarf, the Draco Dwarf, and the Ursa Minor Dwarf. Each one of them is a miniature galaxy of its own. It has its own stars, its own history, and its own orbit. For many years, scientists had treated these satellites as neighbors. They were just separate objects that were passing by. But new measurements have now revealed the truth about them. They are not just passing by our galaxy at all. They are gravitationally bound to us, and they are trapped. They are orbiting within the Milky Way's sphere of influence. This discovery has changed everything about our understanding. When you measure how fast a satellite galaxy is orbiting, you can calculate the mass that is holding it in place. More mass means that the orbits will be tighter. Less mass means that the objects will be able to drift away. The satellite galaxies are orbiting at specific distances and speeds. These orbital parameters reveal our total gravitational pull. The Large Magellanic Cloud is sitting 160,000 light-years away. It orbits the Milky Way once every 1.5 billion years. For it to stay in that orbit at that distance, our galaxy must be massive, far more massive than the old estimates had suggested. Researchers have tracked dozens of these satellites and found the same pattern. They are all orbiting much farther out than was expected. They are all moving much faster than was predicted. The only possible explanation for this is that the Milky Way is huge. It is bigger and heavier than we had ever realized. But the real breakthrough came from the discovery of the tidal streams. When a satellite galaxy orbits too close to the Milky Way, our galaxy is able to rip it apart with its gravity. The stars of the smaller galaxy are pulled away in long trails. The Sagittarius dwarf is currently being destroyed in this very way. Its stars are stretching all across the sky in a long stream. It is wrapping around the entire galaxy like a ribbon. These tidal tails are acting as test masses for us. They are showing us where the gravitational field is the strongest. They are showing where it weakens and where the boundary sits. If you map enough of these tidal streams, you can map the edge. You can map the very edge of the entire galaxy. What the scientists found when they did this shocked them. The streams were extending far beyond the supposed galactic edge. Some of them were reaching out past 150,000 light-years. Others were hitting the 200,000 light-year mark. A few hints have suggested that there is material even farther out. The satellites were screaming the truth about our galaxy. The Milky Way is absolutely huge in its size. This discovery had some immediate and profound implications. If our own galaxy is this large, the local group needed redrawing. The space between us and the Andromeda galaxy is smaller than we thought. The gravitational influence of each galaxy is reaching farther. The collisions between them will happen sooner in the future. The mergers between them will start much earlier. Every satellite galaxy has now become a data point for us, and every single orbit has become a measurement tool. Together they have painted a picture of a galactic giant, not the medium-sized spiral galaxy that we had imagined. And here is the most haunting part of this whole story. Some of the satellites are orbiting so far out that we are still discovering them. Every few years, astronomers find another dwarf galaxy that is hiding in their data. Each of these new discoveries is extending our boundary a little farther. How many more of these are still out there waiting to be found? How much bigger does the Milky Way actually get? 200,000 light-years is a number so big it stops having meaning. Your brain cannot process it. It cannot visualize it. Let me make it even worse for you to comprehend. Light is traveling at 186,000 miles per second. In one single year, that light can cross about 6 trillion miles. Now, multiply that number by 200,000. The Milky Way is approximately 1.2 quintillion miles across. That number is still completely meaningless to us. Let me try to explain it in another different way. If you could travel at the speed of light, the absolute speed limit, it would take you 200,000 years to cross the galaxy. When the light that is leaving one edge finally reaches the other side, humans will have evolved from primitive hunter-gatherers into a spacefaring civilization. And then they will have collapsed and evolved again multiple times. Or you can try to put it in this other way. If the Earth was the size of a single grain of sand, the Milky Way would stretch farther than the distance from the Earth to Saturn. Actually, it would be much farther than that distance. Or you can try this way of thinking about it. The light that you are seeing from the far edge of the galaxy, it left that edge before modern humans had even existed. It left before the Neanderthals and before Homo erectus. That light has been traveling since our ancestors were still living in the trees. The sheer scale of this breaks our human intuition. We have evolved to be able to understand distances on a human scale. We can walk for miles, or maybe even hundreds of miles. Our brains have never developed the wiring to comprehend billions of trillions of anything. But here is where it all gets very personal for you. That incomprehensible size matters to you right now today. Doubling the galaxy's size means doubling the volume of space. The volume of a sphere increases with the cube of the radius. If the galaxy is twice as wide, it is 8 times bigger in total volume. That means 8 times more space, 8 times more stars, and it means 8 times more planets for us to search. The old estimate for the number of stars was 200 billion. The new estimate is closer to 400 billion or maybe even more. Every single one of those stars could have its own planets, and every one of those planets could have its own moons, and every one of those moons could have a subsurface ocean. The number of potential homes for life in our galaxy just doubled. Think about what that means for the search for life. If life is a rare phenomenon, 1 in a billion star systems, we have just added 200 billion more chances to find it. If intelligent life exists somewhere out there in the cosmos, we have just doubled the probability of being able to find it, or for them to be able to find us in the future. But the size of the galaxy also changes our own survival timeline. The Andromeda galaxy is heading directly toward us at 70 miles per second. When two galaxies collide, they do not crash like cars. They will merge together over a very long period of time. The stars will pass between each other with very few actually hitting, but the gravitational chaos of the event will reshape everything. Scientists had previously calculated the Andromeda collision. They had calculated that it would begin in 4.5 billion years. A bigger Milky Way means a bigger gravitational reach. The two galaxies will start affecting each other much sooner than we thought. Maybe in 4 billion years or maybe even less. Your descendants, if humanity is able to survive that long, they will be able to watch the night sky completely transform. Andromeda will grow larger and brighter in the sky. It will eventually fill half of the visible night sky. Then the two galaxies will dance around each other. Their spirals will be intertwining with each other, before they finally settle into one massive elliptical galaxy. 200,000 light years is not just a number. It is your future, it is your past, and it is the stage where every single human story has ever been told. And we have just realized that the stage is twice as big as we had ever thought it was. Andromeda is coming for us, and this is not a theory. This is a confirmed fact that is based on real measurements. Our neighboring galaxy is racing toward us at 70 miles per second. The collision between the two of them is inevitable. For many decades, scientists had calculated the impact. They had calculated it would happen in approximately 4.5 billion years. You could mark your calendars for this cosmic event, except that those calculations had assumed the old galactic sizes, a smaller Milky Way, a smaller gravitational reach, and more empty space between us and the Andromeda galaxy. A bigger Milky Way completely changes the timeline of this event. The force of gravity is able to reach much farther out. The two galaxies will start pulling on each other sooner than we predicted. Their massive dark matter halos will be the first to interact. These halos are stretching for hundreds of thousands of light years outward. When those vast halos finally touch each other, the great cosmic collision will have officially begun. Think of two people that are walking toward each other. If they are both larger than you had thought they were, they are going to bump into each other much sooner. The same principle applies on a grand galactic scale. New models have suggested that the interaction could begin sooner. It could begin in under 4 billion years from now, maybe even in 3.5 billion years from now. The exact timeline will depend on precise measurements. Measurements that we are still in the process of collecting, but the trend in the data is very clear to see. Bigger galaxies mean that the contact will be earlier. Here is what will happen during a galactic collision. First, the outer halos of the two galaxies will start to merge. The dark matter will be interpenetrating with itself. This phase of the merger will be completely invisible, but it will be gravitationally very intense. The stars will begin to feel the pull from both galactic centers. Their orbits will become destabilized and chaos will begin. Some of the stars will be flung out into intergalactic space. Others will be plunging in toward the cores of the galaxies. Then, the visible disks of the two galaxies will collide. This will not be a crash, but more like two clouds passing through each other. The stars are so far apart that direct impacts are incredibly rare. You could fit millions of Earths between the neighboring stars. But the gravitational chaos of the event will be real. Star formation will explode all across both of the galaxies. The gas clouds will be compressed by the collision. New stars will ignite all across both of the galaxies. The Milky Way and Andromeda will then orbit each other multiple times. They will be dancing and spiraling around each other. Each of these passes will strip away more and more material. The tidal forces will shred the beautiful spiral arms. Stellar streams will be scattered in every direction. The once elegant structures will become warped and distorted. They will become completely unrecognizable to us. Eventually, maybe 1 billion years after the first contact, the two galaxies will finally merge completely into one. The result of this merger will be a massive elliptical galaxy. There will be no more spiral arms and no more organized disk. Just a giant blob of 4 trillion stars orbiting in random directions. Astronomers have already come up with a name for this future galaxy. They have named it Milky Way, a cute name for the death of 2 spirals. But here is the most critical question for us. Will the Earth be able to survive this cosmic event? Will our Sun be able to survive it as well? Will humanity be around to be able to see it happen? Let us start with the good news first. The Sun will most likely be able to survive the merger. It is sitting far enough from the galactic center. It will probably be able to avoid the most violent regions. The Earth might be flung into a different orbit, or it might be ejected entirely into intergalactic space, or it might just stay roughly where it is right now. The odds are in favor of the survival of our solar system. Now, for the bad news about all of this. The Sun will be long dead by the time that this happens. Our star has about 5 billion years of fuel left. The Andromeda collision will happen before the Sun dies, but it will be a very close call for us. We might be able to get a front row seat to the early stages. A bigger Milky Way has moved up that timeline for us. The big show is going to be starting much sooner. And here is the part that nobody ever talks about. What if the Andromeda galaxy is also bigger than we have measured? Their estimates of its size could be wrong as well. If both of the galaxies are larger than we thought, the collision between them will happen even sooner. The gravitational chaos will become much more intense. The final merged galaxy will become even more massive. We are already starting to see the early signs of this. Andromeda's vast halo is extending out toward us, and our own halo is reaching out toward them as well. The halos of the two galaxies might already be touching. The collision might have already begun slowly and invisibly. It would be happening in the dark matter that envelops both galaxies. 4 billion years sounds like forever to us, but on cosmic timescales, it is just tomorrow. And tomorrow has just gotten a little bit closer. Mass is the key to everything in the universe, and the Milky Way has just gained a lot of weight. Trillions upon trillions of solar masses have appeared in the data. The old estimate for our galaxy's mass was about 1.5 trillion. Most of that was in the form of dark matter. The new measurements are around 4 trillion solar masses. We have tripled the mass estimate in less than a decade. Here is what a single solar mass actually means. Our own sun weighs about 2 quintillion kilograms. It is a number so large that it becomes completely abstract. It is just one single solar mass in astronomical terms. For comparison, the Earth weighs 300,000 times less than the Sunday. Jupiter weighs 1,000 times less than the Sun. Everything in our solar system except for the Sunday It adds up to barely 1% of one single solar mass. Now multiply the Sun's mass by 4 trillion. That is the total mass of the Milky Way galaxy. It is a true gravitational giant in the universe. Where did all of this extra mass come from? Did the galaxy suddenly gain a whole lot of weight? Did all of this new material appear from absolutely nothing? Obviously not, as it was always there in the first place. We just were not able to measure it correctly before. Most of this extra mass is in the form of dark matter. It is invisible, undetectable, except through its gravity. The old measurements had focused on the visible stars and gas. They had estimated the dark matter indirectly. They used the galactic rotation curves to do so. The stars are orbiting the center at speeds that are determined by mass. If you measure the speeds, you can calculate the mass. But those measurements only sampled the inner part of the galaxy, the region where the stars are common and observations are easy. Nobody had accurately measured the outer halo of the galaxy, the region where the dark matter completely dominates. That was the fundamental mistake that had been made. New techniques have completely changed everything for us. Satellite galaxy orbits are providing direct mass measurements. They are doing so at very huge distances from the center. Stellar streams are mapping the gravitational field in the outer regions. Computer simulations are comparing our galaxy to virtual ones. All of these different methods are agreeing with each other. 4 trillion solar masses is the new estimate. The Milky Way is a true heavyweight in the cosmos. This has some enormous implications for our understanding. More mass means that there is stronger gravity. Stronger gravity means that we can hold more satellite galaxies. We can strip stars from our passing neighbors more easily. We are able to dominate the local group more completely. Andromeda was always considered to be the bigger sibling, the alpha galaxy of our local neighborhood. But the new measurements are suggesting that we might be equals, or that we might even be larger than Andromeda. The Milky Way and Andromeda are weighing roughly the same, 4 trillion solar masses, each 2 galactic superpowers, and they are on a direct collision course with each other. More mass also changes how we think that we formed. Galaxies are known to grow by eating the smaller galaxies. The bigger you are, the more you have consumed in the past. A 4 trillion solar mass galaxy has a very bloody history. We have devoured hundreds of dwarf galaxies, maybe thousands. Every single satellite stream in the halo is evidence of a meal, a galaxy that got too close and then paid the price. The Sagittarius dwarf galaxy is being eaten right now. It is being torn apart, digested, and its stars scattered. In a few 100 million years, no trace of it will remain, except for some ghosts that are in the astronomical data. This is how all of the galaxies in the universe grow. It is through cannibalism and galactic empire building. But here is the most terrifying part of all of this. If we are 4 trillion solar masses, and most of that is dark matter, we are living in a galaxy that is made mostly of invisible material. 90% of everything that is around us is something we cannot see. We cannot touch it, and we cannot directly detect it. You think that you know where you are living in the universe. You think that you understand your own cosmic neighborhood, but you are completely wrong in that assumption. You are swimming in a vast ocean of dark matter, and you cannot even feel the water around you. 4 trillion solar masses of mostly invisible material. That is our home. That is the Milky Way galaxy. And we have just realized how enormous it truly is. The galaxy does not end where the visible stars stop. It just keeps on going and going, far beyond anything visible. It goes into the realm of pure and invisible dark matter. Scientists are calling this the dark matter halo of the galaxy. A massive spherical cloud of invisible particles. It is surrounding the entire visible part of the galaxy. This halo is not just some minor feature of the galaxy. It is the dominant structure, the foundation, and the cage. The cage that is holding everything together with its gravity. Conservative estimates are putting the halo's radius at a huge distance. at 250,000 light-years from the center. This is the virial radius where material is gravitationally bound, but some of the models are suggesting that the halo extends much farther, 400,000 light-years or even 600,000. Some calculations have pushed it past 1 million light-years. 1 million light-years, a truly staggering distance. If this is true, that would make the Milky Way 20 times wider. 20 times wider than the old textbook measurements. 20 times more space under our own gravitational control. Picture the immense scale of this for a moment. The Andromeda galaxy is sitting 2.5 million light-years away. If our dark matter halo reaches 1 million light-years out, and Andromeda's halo does the very same thing, only 500,000 light-years of truly empty space would separate us. The halos of the two galaxies might already be touching each other. Two invisible clouds of dark matter that are interpenetrating. They are mixing together and preparing for the eventual collision. We cannot see this halo directly with our own eyes. Dark matter does not emit light, and it does not absorb light. It does not interact with electromagnetic radiation at all. It only interacts through the force of gravity. But that gravity is real, it is measurable, and it is powerful. Researchers are mapping this halo using indirect methods. Satellite galaxy orbits are revealing where the mass is concentrating. Gravitational lensing is showing where the space is being curved. Computer simulations are predicting how the dark matter should be distributed. All of the evidence is pointing to the very same structure. A massive spherical halo that is dense near the center, and it is thinning gradually out toward the edges. There is no sharp boundary, just a slow fade into intergalactic space. The halo is able to explain many of the mysteries. Why do the stars at the galaxy's edge orbit so fast? The immense gravity of the halo is holding them in. Why do the galaxies spin without flying apart? The halo is providing all of the extra mass that is needed. Why can we see more gravitational lensing than visible matter explains? The halo is bending the space with its gravity. But here is what makes this truly strange to think about. You are inside of this halo right at this very moment. Dark matter is surrounding you, and it is passing through you. The Earth is swimming through a sea of dark matter particles. They are moving at hundreds of miles per second. Trillions of them are streaming through your body every single second, and you do not feel anything at all from them. They are passing through normal matter like they are ghosts. Scientists are trying to detect dark matter directly. Deep underground laboratories are waiting for a dark matter particle, waiting for it to bounce off of a normal atom. So far, they have not found anything at all. The particles are too shy, too rare, or we are looking in the wrong way. If the halo truly extends for 1 million light-years, the Milky Way is claiming an enormous volume of space. Most of the local group is falling within our sphere of influence. We are not just a galaxy, we are a galactic empire, a superstructure of invisible mass that is dominating everything. And if our own halo is this large and massive, every other galaxy in the universe must have one too. The universe is not mostly empty space that is dotted with galaxies. The universe is mostly dark matter halos with galaxies embedded. They are embedded in their centers like the seeds in a fruit. Everything that we can see is just a tiny fraction of what exists. The visible universe is just the decoration on an invisible scaffold. 1 million light-years of darkness that is the Milky Way. That is our home in the vastness of the cosmos, and we are just beginning to understand how enormous it is. The galaxy is spinning much too fast for its own good. It should be flying apart into 1 million different pieces. The stars that are at the outer edge are orbiting at very high speeds. Speeds that make no sense at all to us. They should be escaping into the vastness of intergalactic space. They should be obeying Kepler's laws of planetary motion. They should be slowing down as you move away from the center. But they do not, and nobody fully knows why this is. Here is the fundamental problem that this presents. In our own solar system, the planets farther from the Sun orbit slower. Mercury is racing around in just 88 days. The Earth takes 365 days to make one orbit. Neptune takes 165 years to do the same. The farther out you go, the weaker the Sun's gravity becomes, and the slower the orbit of the planet will be. This is just basic physics that we have known for a long time. Isaac Newton was able to figure all of this out 300 years ago. The galaxies should be working in the very same way. Most of the mass in a galaxy is sitting near the center. The stars that are farther out should be feeling weaker gravity. Their orbits should be slowing down as a result. When you measure their speeds, you should see a nice curve, a curve that is decreasing with the distance from the center. Except that that is not what happens in reality. The stars at the very edge of the galaxy are orbiting at the same speed as the stars that are closer in. The rotation curve of the galaxy stays completely flat. This is impossible unless there is more mass out there. More mass out there than what we can actually see. Dark matter, it is always dark matter in the end. The invisible halo is providing all of the extra mass. It is extending far beyond the visible stars in the galaxy. It is keeping the outer objects moving very fast. The flat rotation curve is the smoking gun in this case. It is the proof that dark matter exists in huge quantities. But here is where things start to get very strange. Even when we account for all of the dark matter, the speeds of the stars are still higher than predicted. Some of the stars in the outer halo are moving at 130 miles per second. Others are hitting 150 miles per second. These velocities are barely below the escape velocity of the galaxy. The stars are almost fast enough to leave the galaxy entirely. Why are they orbiting so close to the edge of escape? What fine-tuned mechanism is keeping them bound but just barely? This is what is known as the escape velocity problem. And it is a problem that is haunting all of the astronomers. One possibility is that we are still underestimating the galaxy's mass. Maybe there is even more dark matter than our current models suggest. Maybe the halo is much denser at the edges than we think. Maybe our mass calculations are still completely wrong. Another possibility is that the galaxy has recently grown. If the Milky Way devoured a large dwarf galaxy in the past, the merger could have injected stars into very fast orbits. These stars have not yet had the time to settle into stable paths. They are still carrying all of the energy from the collision. The evidence is supporting this particular idea. The Sagittarius dwarf galaxy is being torn apart right now. Its stars are being scattered into the Milky Way's halo at high speeds. In 1 billion years from now, those stars will look like native halo stars. They will be fast, barely bound, and very mysterious. But we have caught this one in the act of happening. We are able to see it happening right before our eyes. But what comes next in this story is even stranger. Some of the stars in the galaxy are moving too slow. They are like hypervelocity stars, but in reverse. They are objects that should be orbiting much faster based on their location. But they are not. They are just drifting along slowly. They are like they are trapped in some kind of cosmic molasses. Nobody has a good explanation for these stars either. The rotation curve of the galaxy should be a simple thing. You measure the speeds, you calculate the mass, and everything should fit. Instead, every new measurement is revealing more anomalies, more outliers, and more stars that are doing things they should not. This is where all of our dark matter theories are being tested. Different models of dark matter are predicting different rotation curves. Warm dark matter is known to produce smoother profiles. Cold dark matter is known to create lumpier structures. Self-interacting dark matter behaves differently in the galactic cores. So far, the cold dark matter model seems to fit the best. But the fit is not completely perfect by any means. Some discrepancies are still remaining in the data. They are small ones, and they are nagging ones. The kind of discrepancies that might be pointing toward new physics. Or they might just be a simple measurement error. The galaxy is spinning much faster than it should be. The stars are orbiting at speeds that are defying our simple explanations. and the larger galactic size is making the problem even worse. More volume, more stars, and more weird velocities to explain. Physics seems to work everywhere else in the universe. It works in solar systems, in star clusters, and in distant galaxies. But in our own cosmic backyard in the Milky Way's rotation curve, something is still not quite adding up for us. The Milky Way has 4 major spiral arms in its structure. Or maybe it has 5 of them, or maybe it has 6. Astronomers are still arguing about this very question. For many decades, the textbook answer was 4 arms. The Scutum Centaurus arm, the Norma arm, and the Cygnus arm. The Perseus arm and the Sagittarius arm as well. Each of these arms is a river of stars, gas, and dust. They are spiraling outward from the galactic center. These arms are tracing the regions where new stars are born. They are bright, dense, and they are easy to spot. Then the better telescopes started to arrive on the scene. Infrared instruments that can see through the thick dust. Radio telescopes that can map the hydrogen gas in the galaxy. Space-based observatories that are above the atmospheric interference. Each of these new tools has revealed features that we had missed. The far 3 kiloparsec arm appeared first in the data. This is a minor spiral arm that is hiding behind the galactic core. We could not see it with our optical telescopes. This is because the center of the galaxy was blocking our view, but the infrared instruments were able to cut right through the dust. And there it was, an entire new spiral arm, thousands of light years long. It had been right under our noses the entire time. Then came the hints of other different structures. The local arm where our own solar system is sitting. It might actually be a major arm, not just a minor spur. New observations are suggesting that it is connected to larger structures. What we had thought was just a small branch. It might actually be a whole and entire limb of the galaxy. The outer arm of the galaxy has posed another mystery. It is sitting at the extreme edge of the visible part of the galaxy. Some researchers had thought that it was just scattered stars, that there was no real structure there at all. But detailed mapping of the region has revealed organized spiral patterns that are extending far into the outer regions. The galaxy has structure in places where we had thought it was empty. But here is the truly bizarre part of all of this. Nobody knows how the spiral arms are able to form. We are able to see them in almost every disk galaxy. They are beautiful and elegant spiral structures, but the physics that is behind them remains murky. Here is the problem that they are presenting to us. The stars are orbiting the galactic center at different speeds. The inner stars are orbiting much faster than the outer stars. If the spiral arms were just concentrations of stars, they would wind up tighter and tighter over time. It would be like stirring cream into your coffee. Within a few rotations of the galaxy, the arms should blur. They should blur into a smooth and featureless disk. But they do not, as the spiral arms are able to persist for billions of years. This suggests that they are not material structures. They are what are known as density waves in the disk, regions where the stars are temporarily bunching up. This is creating the illusion of a solid arm. It is like cars that are bunching up in a traffic jam. The cars are moving through the jam, but the jam stays in place. The density wave theory works very well mathematically, but our observations are keeping on finding exceptions to it. Some of the arms have too many young blue stars. Others are showing gaps where there should be stars. The outer arm of the galaxy appears to be too massive to be just a simple density wave in the disk. It might be a real material structure in the galaxy, material that was pulled out during a galactic collision, a collision that happened millions of years ago. The bigger Milky Way size is complicating everything. More space means that there is more room for structure. The arms can extend farther out than we had thought. New arms can form in regions that we had thought were empty. The spiral pattern of the galaxy is becoming more complex. Recent surveys that have used the Gaia spacecraft have mapped 1 billion stars. They have done so with an incredible level of precision. the data has revealed a great deal of substructure within the arms. There are branches, spurs, and gaps in the arms. The spiral pattern of the galaxy is not clean and neat. It is very messy and chaotic, like tree branches that are growing in every single direction. Some researchers are now arguing that the Milky Way is not a grand design spiral. It might be what is known as a flocculent spiral, a galaxy with patchy and poorly defined spiral arms. This would explain why the different surveys are finding different arm counts. Everyone is seeing different features depending on what they are measuring. The debate about this is still continuing today. More telescopes, more data, and more arguments at conferences. But one thing is certain: the Milky Way is more complex. More complex than the simple four-arm diagram in the textbooks. Hidden structures are filling the galaxy everywhere. Arms that we had missed for many decades are now visible. And if we had missed entire spiral arms in our own galaxy, what else have we overlooked in the darkness? What other features are hiding, waiting for the right instrument to finally reveal them? Draw a line that is marking the very edge of the galaxy. That sounds like a simple thing to do, but it is impossible. Galaxies do not have boundaries like countries or continents. There is no border wall, and there is no sign that is saying, "Now leaving the Milky Way." The stars are just thinning out very gradually, slowly, until there are none of them left at all. Or maybe just a few scattered stragglers are remaining. Where exactly does that become? Not the galaxy. This is not just some kind of philosophical question. It is a very practical problem for the astronomers. Astronomers are needing a definition, a standard measurement, a way to be able to compare the different galaxies. But nature does not seem to cooperate with this need. The universe does not care about our need for clean categories. Several different definitions for this are existing, but none of them are perfect by any means at all. The optical radius is marking where the visible stars become too faint to see. This is giving you the bright disk of the galaxy, the obvious part. 100,000 light-years for the Milky Way galaxy. But this is ignoring all of the faint stars in the galaxy, the dim dwarf stars, and the scattered halo objects. It is like measuring a city by only counting the skyscrapers, and you are ignoring all of the houses in the suburbs. The virial radius is a much more scientific definition. It is marking where the objects are gravitationally bound to the galaxy. Inside of this radius, the stars are orbiting the center. Outside of this radius, they are drifting freely in space. For the Milky Way, this gives about 250,000 light-years. This is much better, but even this has some problems. Some of the stars that are outside of the virial radius are still moving. They are still moving with the galaxy through space. They are sharing our motion through the vast universe. They were formed here, so are they a part of the galaxy or not? The virial radius is saying no, but common sense is saying maybe. Then there is the vast dark matter halo to consider. It is extending far beyond everything else in the galaxy. If the halo is reaching 1 million light-years out, is that the real edge? Most of the astronomers are saying no to this idea. The halo is fading so gradually that choosing any boundary is arbitrary. It is like trying to mark where the Earth's atmosphere ends. Technically, it is extending for thousands of miles up, but practically, it is gone after about 100 miles. Where do you draw the line for something like that? The situation is getting even worse when you consider the galactic winds. The Milky Way is producing massive outflows of gas. Supernovas are exploding, and the stars are shedding their material. This gas is blowing outward into intergalactic space. It is going for hundreds of thousands of light-years out. Is that material still a part of our galaxy or not? Some of it will eventually fall back to the galaxy. The gravity is pulling it back down over time. The galaxy is recycling its gas over billions of years, but some of it is able to escape, forever lost to the void. At what point does the gas stop being Milky Way gas, and at what point does it become the intergalactic medium? The Magellanic Stream is adding another complication. The large and small Magellanic Clouds are leaking gas. They are leaking gas as they are orbiting around us. This gas is forming a long stream that is stretching across the sky. Is that stream a part of the Magellanic Clouds or the Milky Way, or is it a part of neither of them at all? All three of these answers have their own defenders. Andromeda is posing the very same problem from the other direction. Its dark matter halo might already be touching ours. When two of these halos are overlapping with each other, where does one of the galaxies end and the other begin? The space that is between them is becoming a shared territory. It is co-owned and it is disputed between the two. This is not just a matter of semantics for us. The definition is affecting the mass estimates of the galaxies. It is affecting the size comparisons that we are making. It is affecting our understanding of when the Andromeda collision truly begins. If the halos are already in the process of merging, the collision has already started millions of years ago. We are living inside of it right at this very moment. Most of the astronomers are settling on practical definitions. The disk is ending where the star formation is stopping. The halo is ending at the defined virial radius. The dark matter is extending as far as the simulations are suggesting. Each of these definitions is serving a different purpose, but none of them are perfectly capturing the reality. Here is the truth of the matter for you to consider. The Milky Way is not an object, it is a region. It is a zone of influence, a gravitational neighborhood. It has a dense core, a structured middle, and a diffuse edge. And beyond that edge, it is fading into something else. 200,000 light-years is our current best answer. But if you ask that question again in another 10 years, new measurements will have changed the number for us. They always do, as our science is always improving. The galaxy has no edge because the universe does not work that way. Everything is blending together and everything is connecting. We are living in a cosmos that is without any borders, and we are still learning how to measure it properly. There are stars that are at the very edge of the galaxy. They are moving at some absolutely insane speeds. 130 miles per second, or 150. Some of them are even hitting 200 miles per second. They should be escaping from the galaxy at these speeds. They should be flying off into intergalactic space, but they do not, as something is holding them back. These are what are known as the high-velocity halo stars. They are not the hypervelocity stars which are moving fast enough to escape. The halo stars are moving just under that critical threshold. They are barely bound to the galaxy and are skating on the edge. Finding these stars was a very difficult task for the astronomers. They are faint, distant, and they are scattered across a huge volume. But the surveys like Gaia have been tracking millions of stars. They have been doing so with an incredible level of precision. You measure the position, you measure the motion, and you calculate the velocity. Some of the stars lit up the red flags immediately. One star that is traveling through the outer halo is moving at a high speed. It is moving at 198 miles per second. The galaxy's escape velocity at that particular location, it is roughly 200 miles per second, very close. This star is just 2 miles per second away from leaving forever. It is like a rocket that is barely being held by the Earth's gravity. One single small push and it will be gone for good. Why are so many of the stars orbiting so close to the escape velocity? This is not just a random chance, as something has put them there. Something has given them that specific amount of energy. But what could that something possibly have been? Galactic collisions are offering one possible answer. When the Milky Way was eating all of the smaller galaxies, the collisions were injecting a great deal of energy into the system. The stars from the dwarf galaxies were receiving huge velocity kicks. Some of them were able to escape, while others settled into fast orbits. These survivors are now populating the halo of the galaxy. The Sagittarius dwarf galaxy is providing the evidence. Its stars are being scattered at very high speeds, as the Milky Way is tearing it apart with its gravity. In 1 billion years from now, those stars will be indistinguishable. They will be indistinguishable from the other halo stars. They will be fast, ancient, and very mysterious. But we have been able to catch this one in the act. We are able to see it happening right before our eyes. Another possibility involves what are known as three-body interactions. When two stars are passing near a third object, the gravitational interactions can fling one of the stars outward. It can fling it outward at a very high speed. This is known to happen in very dense star clusters. Occasionally, a star can get ejected with enough energy to be able to reach the galactic halo. Most of them will escape, but a few will land in that sweet spot. They will be fast, but not too fast to escape. Black holes are complicating everything in this picture. If a star is passing close to a massive black hole, the gravitational slingshot effect can accelerate it. It can accelerate it to some absolutely enormous speeds. The supermassive black hole at the galaxy's center is huge. It weighs 4 million suns, a true cosmic beast. Any star that is venturing too close to it will either be eaten, or it will be flung away from the center very violently. We have found several of the hypervelocity stars. They are leaving the galaxy at speeds of over 400 miles per second. These stars are definitely escaping from the galaxy. There is no question about that at all for us. The calculations are tracing their paths back to the galactic center. Something near the black hole must have kicked them out. Maybe they were in binary pairs and the black hole captured one. It captured one of the stars while it was ejecting the other. But the barely bound stars are posing a different puzzle. They are not coming from the center of the galaxy. They are orbiting far out in the vast halo of the galaxy. Their speeds are high, but they are not extreme. They seem to be comfortable at the very edge of the galaxy's gravity well. One theory is suggesting that the dark matter halo is lumpy. It is lumpier than we have been thinking it is. Concentrations of dark matter at specific distances could be creating stable orbits. Stable orbits at very high velocities for the stars. The stars would then be settling into these orbits naturally. This would explain why so many of the halo stars are moving at similar speeds. They are trapped in a kind of resonance with the dark matter distribution. Testing this particular theory is a very hard thing to do. We cannot see the dark matter directly with our telescopes. We can only infer its distribution from how the stars are moving. But if the halo is lumpy, we should be able to see groupings. We should see clusters of high-velocity stars that are orbiting together. Some of the surveys are hinting at this possibility, but others are finding more random distributions of the stars. The data that we have is very messy, and it is hard to interpret. Here is what we know for certain about all of this. The galaxy's outer regions are much wilder than we had expected. The stars are moving much faster than our simple models are predicting. The boundary between being bound and unbound is very thin. Barely a few miles per second is separating, staying from leaving. If the galaxy is larger than we had thought it was, more of the stars will be living in this very dangerous zone. More objects will be skating at the very edge of the galaxy. And there will be more potential escapees from our galaxy. And understanding why they are staying is revealing something deep about the structure of our galaxy, something about dark matter, and about how gravity works. How it works at these absolutely enormous scales. Fast stars at the very edge of our own galaxy. They are being held there by some kind of invisible mass, and they are moving at some absolutely impossible speeds. And we are only just beginning to understand what is keeping them here. The Milky Way is not a special galaxy in any way. If we have measured our own galaxy wrong for so long, we have probably measured all of the other galaxies wrong too. This is the terrifying implication of this new discovery. The realization that is making astronomers stay up at night. They are recalculating everything that they had thought they knew. Every single galaxy in the entire universe might be twice as large as what has been recorded in our catalogues. The entire cosmic census is in need of a complete rewriting. Here is the reason why this matters so much to us. Astronomers are using galaxies to understand the universe, how all of the matter in it is being distributed, how all of the structure in it is able to form, and how dark energy is affecting the cosmic expansion. If all of the galaxies are bigger than we had thought, every single one of our calculations is going to change. The masses of the galaxies are determining how they interact. Bigger galaxies are having a stronger gravitational pull. They are able to strip the stars from smaller neighbors more easily. They are able to dominate their local groups more completely. And they are able to form into clusters in a different way. If you recalculate the masses, you have to recalculate galaxy evolution. The problem is extending to all of our distance measurements. Astronomers are using certain types of galaxies as standard candles. These are objects with a known and predictable brightness. You measure how bright they appear to be in the sky, and then you can calculate how far away they must be. But if those galaxies are bigger, their brightness will change, the distances will change, and the expansion rate of the universe will change. Our measurements of dark energy are depending on precise distance calculations. Any error in these measurements will propagate through every model. If the galaxies are universally larger than we thought, the calculations for dark energy are going to shift. The universe might be expanding faster or slower than we think. Researchers are now revisiting all of the galaxy surveys, the Sloan Digital Sky Survey and the 2-micron All-Sky Survey. Every single major catalogue of galaxies is being re-examined. They are applying the new measurement techniques to the old data. They are accounting for the dark matter halos now. They are using stellar streams and satellite galaxies where they are available. The preliminary results of this work have been disturbing. Many of the galaxies are appearing to be larger than before. Some of them are 50% bigger on average. Others have even doubled in their size, just like the Milky Way. The trend that they are seeing is very consistent. We have been systematically underestimating the size of galaxies. Andromeda is bigger, and Triangulum is bigger as well. Every major galaxy in the local group is in need of remeasurement, and if the local galaxies are bigger, the distant galaxies probably are too. The whole cosmic web might be much denser than we had realized. This has some serious implications for our understanding of dark matter. If the galaxies are bigger, they must contain more dark matter. The ratio of dark matter to normal matter is going to shift. This will affect our theories of how galaxies are able to form. It will affect our predictions about how the universe has evolved. It will affect whether our cosmological models even work at all. Some researchers have suggested that the discrepancy explains long-standing problems. The missing satellite problem, for example, could be solved. The simulations are predicting that large galaxies should have hundreds of satellites, but we are only observing dozens of them around our galaxy. If our galaxy is bigger, its gravity is able to pull farther out. Maybe those missing satellites are existing, but they are orbiting far out. They are orbiting so far out that we have not been able to find them yet. Another puzzle is involving the galaxy rotation curves. Many of the galaxies are showing the same flat rotation pattern as the Milky Way. The stars at the edge are orbiting much too fast. This is the reason why dark matter was hypothesized in the first place. But if the galaxies are bigger with more extensive dark matter halos, the rotation curves are making a lot more sense now. The physics of the situation is fitting much better, but recounting the universe is creating some new problems. If the galaxies are bigger, the space between them is smaller. The universe is becoming a much more crowded place. Galaxy interactions are happening more often than we thought, and the collisions are occurring much sooner in time. The timeline of cosmic evolution is speeding up for us. This is affecting our understanding of the galaxy clusters. These are large groups of galaxies that are bound by gravity. If each of the galaxies is bigger, their gravitational interactions are more complex. The dynamics of the clusters are going to change. The mass estimates are going to shift as a result, and the dark matter distributions are in need of recalculation. Even the very early universe is being affected by this. Astronomers are using distant galaxies to study cosmic history. Galaxies that were forming billions of years ago. If those primordial galaxies were larger than we have measured, They must have formed much faster than we had thought. The structure in the universe must have assembled more quickly. The universe was more mature at earlier times than our models are suggesting. The implications are cascading through every single field of astronomy. Stellar population studies, galaxy morphology, and active galactic nuclei. Supermassive black hole evolution is also being affected. Everything is connecting to the size of the galaxies. We are now in the process of recounting the entire universe. Every galaxy, every cluster, and every single structure. We are starting from scratch with our better measurements. And the universe that is emerging is bigger and denser. And it is more complex than we had ever imagined. The Milky Way was just the beginning of this, the first domino, and all of the rest of them are now falling. The Milky Way is spinning around a single point in space. It is not the supermassive black hole, and it is not the visible core. It is the center of mass of the entire galaxy. And we have just realized that that point is not where we thought it was. The center of mass is a simple concept in principle. It is the balance point of an object, the spot where all the mass averages out. For a simple ruler, it is in the very middle. For the Earth and the Moon, it is a point that is inside the Earth, but it is offset from the center because of the Moon's pull. For the galaxy, it is the location around which everything is orbiting. Astronomers had assumed that the center of mass was at the galactic core. This makes a lot of sense as most of the visible stars are there. The supermassive black hole is also sitting there. Everything seems to be pointing toward the center. But that assumption was ignoring the dark matter. Dark matter is not concentrated at the very core. It is forming a massive halo around the entire galaxy. This halo is not perfectly symmetric in its shape. It is lumpy, and it is denser in some directions than others. The distribution of the dark matter is shifting the center of mass. It is shifting it away from the visible center of the galaxy. When the scientists recalculated this using the larger galactic size, and they used the updated dark matter distributions, the center of mass of the galaxy moved its position. It did not move dramatically, not by thousands of light years, but it moved enough to matter for our calculations. A few hundred light years, or maybe even 1,000. This sounds like a very small distance in cosmic terms, but in human terms it is absolutely enormous. The center of mass has shifted farther than the entire distance from the Earth, farther than the distance to the very nearest star, farther than dozens of solar systems that are lined up end to end. Why does this small shift matter so much to us? Everything in the galaxy is orbiting the center of mass. It is not orbiting the visible center of the galaxy. The stellar orbits are depending on where the true balance point is sitting. The satellite galaxies are also orbiting around this point. The motions of the stars that are near the core are revealing the center. They are revealing the center of mass location for us. Measuring this shift in the center is a very difficult thing to do. You are needing precise velocities for the stars throughout the galaxy. You are needing accurate dark matter maps of the galaxy. You are needing computer simulations to model the entire gravitational field. Only recently have our instruments been good enough to detect the offset. The Gaia spacecraft has provided the big breakthrough for us. It has measured the positions and velocities for over 1 billion stars. It has done so with an incredible level of precision. Researchers have fed this data into their simulation, and they have calculated the gravitational center of the galaxy. The results of this work have been very surprising. The center of mass does not align perfectly with the black hole. This has some serious implications for our own orbit. The solar system is orbiting the galactic center once every 230 million years. This is what is known as a single galactic year. But if the center of mass is offset from the core, our actual orbital path is slightly different than we have calculated. We might be completing an orbit a little faster or slower than we thought. The offset is also affecting how we are modeling the galaxy. The simulations are assuming perfect symmetry for simplicity. A core at the exact center and dark matter that is distributed evenly. But the reality of the situation is much messier than that. The Milky Way has likely formed through the mergers with smaller galaxies. Those collisions have left behind some scars on our galaxy. Asymmetries in the dark matter distribution are offsetting the mass. The Sagittarius dwarf galaxy is currently falling into the Milky Way. As it is being torn apart by our gravity, its mass is affecting us. It is affecting our own center of gravity, but not by much. The dwarf is very small compared to the entire galaxy. But over millions of years, these interactions are shifting the balance. They are shifting the balance point of the galaxy around. Some researchers have suggested that the center of mass is oscillating. It is moving back and forth slightly as the galaxies are falling in. The Milky Way is not a static structure in the universe. It is dynamic, it is constantly evolving, and it is constantly eating. And every single meal that it has is shifting the balance. Here is the strangest part of all of this to consider. If the center of mass is offset from the black hole, what does that mean for the black hole itself? Supermassive black holes are supposed to be sitting at the galactic centers. This is because they are forming there in the first place. They are growing by eating the material that is falling toward the center. If the center of mass is elsewhere, why is the black hole where it is? One possibility is that the black hole is predating the current structure. It formed when the galaxy was much smaller and more symmetric. As the Milky Way grew through all of its mergers, the mass distribution of the galaxy changed over time. The center of mass shifted, but the black hole stayed put. It stayed put because it is so incredibly massive. Nothing can easily move 4 million solar masses of material. Another possibility is that the offset is only temporary. Over billions of years, the galaxy will settle into a more symmetric state. The center of mass will then drift back toward the core. The black hole will then remain at the very center. The equilibrium of the galaxy will finally be restored. But for now, in this snapshot of galactic evolution, the balance point of the galaxy is slightly askew. The Milky Way is spinning around a point that is not quite where we expected. The galaxy has just gotten bigger than we had ever thought. And with that growth has come a very subtle shift, a subtle change in the center of everything for us. It is small in cosmic terms, but enormous in human terms. And we are only just beginning to measure what that shift means. Galaxy collisions are not what you are thinking they are. There are no explosions, there are no fireballs, and there are no dramatic crashes. Just a slow-motion gravitational ballet that is stretching across millions of years. But the scale of the galaxies changes everything about this. A bigger galaxy is going to collide differently than a small one. The physics of the situation is staying the same. But the outcomes of the collision are transformed completely. When two small galaxies are colliding with each other, the interaction between them is relatively quick. A few 100 million years or maybe a billion years. They will merge, they will settle, and then they will move on. But when two massive galaxies like the Milky Way and Andromeda collide, the process is going to take a much longer time. The increased mass of the galaxies means that there is stronger gravity, and stronger gravity means that there are more complex interactions. Here is what is going to happen in a large galaxy collision. The first contact is going to occur when the dark matter halos touch. This is going to happen long before the visible disks are interacting. The halos are extending for hundreds of thousands of light years outward. When they are meeting, the force of gravity is beginning its work. The halos are interpenetrating with each other. The dark matter particles are passing through each other like ghosts. They are not colliding with each other physically, and they are not bouncing. They are simply occupying the very same space at the same time, but their gravity is affecting everything in the process. The stars are feeling the pulls from both of the galactic centers. Their orbits are becoming destabilized, and chaos is beginning. Next, the outer stellar halos are going to be interacting. The stars that are in these regions are already moving very fast. They are barely bound to their home galaxies by gravity. When another massive galaxy is approaching them, some of the stars are going to be flung into intergalactic space. They will be ejected and they will be lost forever. Others are going to be captured by the approaching galaxy. They will be stolen by the other galaxy in the process. The galaxies are going to be starting to exchange their stars. They will be exchanging them like they are trading cards. Then there are the powerful tidal forces to consider. As the galaxies are passing each other in their orbits, gravity is pulling harder on the near side than on the far side. This difference in the force is stretching both of the galaxies. The material is being pulled into long streamers that are called tidal tails. These tails can be extending for millions of light years into space. They are beautiful, they are destructive, and they are proof. They are proof that two giants have fought here in the past. The visible disks of the two galaxies are the last to collide. When they are meeting, something absolutely remarkable is going to happen. The gas clouds in both of the galaxies are going to be compressed. The compressed gas is then going to collapse under its own gravity, and the collapsed gas is going to form new stars. Star formation is going to explode all across both of the galaxies. Millions of new stars are going to ignite in a cosmic fireworks display. Astronomers are calling these galaxies starburst galaxies. They are collisions that are in the process of happening. But here is where the size of the galaxies is mattering the most. Bigger galaxies are having much deeper gravitational wells. They are much harder to be able to escape from. When the material is being pulled into the tidal tails, more of it is going to fall back to the galaxy. Smaller galaxies are losing their material permanently, but the larger galaxies are able to recycle it over time. The Milky Way and Andromeda are going to be shedding their stars, but most of them are eventually going to return. The merger timeline is going to be stretching out for longer too. Small galaxies might be completing their merger in 1 or 2 passes, but the large galaxies are going to be orbiting each other multiple times. 3 passes, 4 passes, or maybe even 5. Each of these orbits is going to be stripping away more material, and each of these passes is going to be driving the cores closer together. Eventually, the friction from the gas and the stars is going to drain energy. The orbital energy of the two galaxies will be gone. The galaxies are then going to spiral inward toward each other. The cores are going to merge, and the final product will be formed. The final product is depending on the mass ratio of the two. When two equal mass giants are colliding with each other, you are going to get a massive elliptical galaxy as the result. The spiral structure of the two galaxies is going to be destroyed completely. The disk stars are going to be scrambled into random orbits. There will be no more elegant spiral arms in the new galaxy, just a giant blob of stars that are moving chaotically. Milky Way, our future merged galaxy, is going to be enormous. It will have 800 billion stars and 4 trillion solar masses. It will be one of the largest galaxies in the entire local group. It will be a true heavyweight in the cosmic scheme of things. But the collision is also going to trigger some other effects. The supermassive black holes at each galactic center are going to merge. 4 million solar masses plus 1 billion solar masses. This is going to equal one massive black hole at the heart of Milky Way. This merger is going to release gravitational waves. Gravitational waves that will be detectable all across the universe. Star formation is going to spike, and then it is going to crash. The initial collision is going to ignite millions of new stars, but the merger is going to consume most of the available gas. After a few billion years, the star formation is going to stop. Milky Way is going to become a red and dead galaxy. It will have old stars and no new ones being formed. It will be slowly fading into the darkness of space. Bigger galaxies are colliding differently than smaller ones. They have longer timelines and more complex interactions. They also have more dramatic and spectacular outcomes. And we are watching the preview of this right now. The Milky Way and Andromeda are already beginning their dance. Their halos might already be touching each other as we speak. The first contact may have already occurred between them. The collision is not coming, it has already begun. And the scale of the galaxies is determining how the story ends. There is a great deal of mass that we cannot account for. Material that should be there, but it is not. Astronomers are calling this the missing mass problem, and it has just gotten 3 times worse for us. Here is the issue that we are facing with this. When you are adding up all of the visible matter in the galaxy, you are getting about 200 billion solar masses. This is the stars, the planets, the gas clouds, and the dust. Everything that we are able to see with our telescopes. Then you are measuring the total gravitational mass. You are using the orbital velocities to do this. And you are getting a value of 4 trillion solar masses. The difference between these two is the dark matter, the invisible mass that is holding the galaxy together. But even when you are accounting for all of the dark matter, the numbers are not balancing out perfectly for us. There should be more normal matter than what we are observing. Simulations of galaxy formation are predicting certain ratios, but our observations are showing much less normal matter. Something is missing from our calculations of the galaxy. This is what is known as the missing baryon problem. Baryons are the normal matter particles like protons and neutrons, the stuff that you and I are made of. The simulations are saying that galaxies should contain a specific amount of baryonic matter based on the cosmic ratio. But when we are counting the stars, the gas, and the dust, we are coming up very short in our calculations. About half of all of the expected baryons are missing. Where did all of this missing material go? Several different possibilities are existing for this. Theory 1 is suggesting that the missing baryons were ejected. Supernovas are exploding, and the stars are producing powerful winds. Active galactic nuclei are blasting out a lot of material. Over billions of years, this outflow could have expelled enormous amounts. The baryons are not missing, they are just outside of the galaxy. They are too diffuse to be able to be detected easily. Theory 2 is proposing that the baryons are hiding. Maybe they are existing as cold gas clouds that are too faint to see. Or they are existing as dim brown dwarfs that are too small to shine. Or they are existing as rogue planets that are drifting through space. They are there, we just cannot find them with our current instruments. Theory 3 is getting a little bit weird with its explanation. Maybe the baryons were never in the galaxy at all. Maybe they are stuck in the intergalactic medium. The space that is between the galaxies is containing thin gas. It is extremely thin, but across enormous volumes it adds up. Perhaps half of all of the universe's baryons are floating in this medium. They have never fallen into the galaxies in the first place. Recent observations are favoring the first of these theories. X-ray telescopes have detected hot gas halos around the galaxies. This gas is too hot to be able to form new stars, but it is too diffuse to be able to be seen easily. It is existing in a weird intermediate state of matter. It is ionized, it is energetic, and it is invisible to most instruments. But it is there, and there is a lot of it. When the scientists were measuring these hot halos, they were finding a significant amount of mass in them. Enough mass to be able to account for much of the missing baryons. Maybe the problem had finally been solved for us, except that the Milky Way has just gotten bigger. This means that it should be having even more baryons. And we are still not being able to find all of them. A 4 trillion solar mass galaxy is needing a specific amount of normal matter based on the cosmic ratios. About 400 billion solar masses of baryons should be there. We are only seeing about 200 billion in the stars and the gas. The rest of them are missing once again for us. Tripling the galactic mass is tripling the missing mass problem. If the galaxy is twice as wide and much more massive, where did all of that extra baryonic matter go? It should be somewhere in the halo or in the disk. It should be somewhere in orbit around the galaxy. But we are not being able to find it with our telescopes. Some researchers are suggesting that the dark matter halo is trapping the hot gas. It is trapping it at some enormous distances from the center, hundreds of thousands of light years out from the core. This gas is so hot and so diffuse that our current X-ray telescopes, they are barely being able to detect it at all. But it is carrying a significant amount of mass. Future missions with better sensitivity might be able to reveal this. They might be able to reveal enormous reservoirs of missing baryons, baryons that are hiding in plain sight from us. Another possibility is involving the circumgalactic medium. This is the zone that is around the galaxy where the material is cycling. Gas that is being ejected by the supernovas is flowing outward. It is cooling down, and then it is falling back to the galaxy. This recycling process is creating a massive reservoir, a reservoir of baryons that is surrounding the galaxy. It is not quite inside of the galaxy and not quite outside. It is in a transitional state between the two. The James Webb Space Telescope is now hunting for these baryons. Its infrared sensitivity is able to detect the warm gas that the other instruments are not able to miss. The early results are hinting at more material in the outer halo, more material than the previous surveys had suggested, but we are needing more data, more observations, and more time. Here is the unsettling truth of this whole situation. We are living in a galaxy where we cannot account for half of the normal matter. We are knowing roughly where the dark matter is located. That is the easy part of this particular puzzle. But the regular matter, the stuff that we are all made of, it is keeping on hiding from us in the darkness. A bigger galaxy is meaning a bigger mystery for us. More missing mass and more unanswered questions. And somewhere out there in the darkness of the halo, 400 billion solar masses of normal matter are waiting to be found by our future telescopes. The Milky Way is not a special galaxy in any way. This fact is keeping on appearing in the field of astronomy. Every time that we are thinking that we are unique, we are discovering that everyone else is the very same. And if our own galaxy is twice as large as we have measured, the spiral galaxies everywhere are facing the same miscalculation. Researchers have tested this particular hypothesis. They have selected a sample of the nearby spiral galaxies, Andromeda and Triangulum galaxies that are close enough for detailed observation. Then they have applied the new measurement techniques to them: satellite galaxy tracking and stellar stream mapping. Dark matter halo calculations have also been used. Every single one of the galaxies has come back larger, not just a little bit larger, but significantly larger, 50% bigger on average than we had thought. Some of them have even doubled in their size, just like the Milky Way. The pattern that they are seeing is universal in its nature. We have been systematically underestimating the size of spiral galaxies. Andromeda has provided the clearest example of this. The old measurement for it was 220,000 light-years across. The new calculations are suggesting 300,000 or maybe even more. The dark matter halo is extending even farther out. Andromeda is a giant, and it is even bigger than we had previously thought. Triangulum is the third largest galaxy in our local group. It has grown from 60,000 light-years to nearly 100,000. Smaller galaxies have also shown similar increases in their size. Every single spiral galaxy that has been examined has come back larger. Why did this happen to us? And why did we get it so wrong? The same reason that we got the Milky Way wrong for so long. The old measurements had focused on the visible light. They had tracked the bright disk where the stars are concentrating. They had ignored the faint and hard-to-see outer regions. They had underestimated the contributions from the dark matter. The mistake that they made was very systematic. It was built into the methodology that they were using. Modern instruments have completely changed everything for us. Wide-field surveys are now mapping the entire galaxies from edge to edge. Infrared detectors are able to see through the thick dust. Deep exposures are able to reveal the faint outer stars. Each of these improvements is extending the measured radius outward, but the real breakthrough has come from the satellite galaxies. Just like the Milky Way is having its satellites, other large spiral galaxies are having them too. Andromeda has dozens of dwarf companion galaxies. Triangulum is also having several of its own. If you track those satellites and you measure their orbits, You can calculate the mass that is holding them in place. The galaxies are then revealing their true sizes to us. Stellar streams are appearing everywhere as well in the data. Andromeda is currently in the process of devouring several small galaxies. The resulting streams are wrapping around it like evidence at a crime scene. These streams are orbiting far beyond the visible disk of the galaxy. They are proving that Andromeda's gravity is reaching farther than the old measurements had suggested for us. The dark matter halos are extending farther than anyone had predicted. When you are accounting for the full halo of the galaxy, not just the inner dense regions of the halo, the spiral galaxies are becoming absolutely enormous. Their spheres of influence are reaching for hundreds of thousands of light years. The space that is between the galaxies is shrinking accordingly. This discovery is having some cascading implications. The galaxy collision rates are in need of a recalculation. If the galaxies are bigger, their halos are overlapping more often. The interactions between them are happening more frequently. The universe is becoming a much more violent and dynamic place. The galaxy number density is also changing as a result. The same volume of space is containing fewer galaxies. If each of the galaxies is larger in its size, this is affecting all of our cosmological models. It is shifting our understanding of how structure is able to form. It is changing our predictions about how the galaxy clusters are evolving. The rotation curves are also making a lot more sense now. Many of the spiral galaxies are showing the flat rotation curves. The stars at the edge are orbiting much too fast. But if the galaxies are bigger with more extensive dark matter halos, the rotation curves are fitting much better with the data. The physics of the situation is working out for us. Some researchers have wondered if the dwarf galaxies are following the same pattern. The early results are suggesting that they are doing so. Even the small galaxies are appearing to be larger than we have measured. Their dark matter halos are extending farther than their visible stars. The size underestimation is affecting the galaxies at every single scale. The elliptical galaxies are remaining less clear for us. They are not having the obvious disks or the spiral arms. Measuring their edges is even harder to do for us. But the preliminary work is suggesting that they are also larger than the traditional estimates had suggested. The problem that we are having is universal in its nature. Here is the bottom line for all of this for you. For many decades, the astronomers were measuring the spiral galaxies. They were using some very incomplete methods to do so. They were counting what they were able to see with their telescopes. They were drawing the boundaries where the stars were becoming faint. They were making some very reasonable assumptions that turned out to be wrong. Every single spiral galaxy in the entire universe is larger than what all of the textbooks are showing. Not just ours, but all of them are much bigger. The cosmic census is in need of a complete revision, and we are only just beginning to understand how much bigger everything is. The local group of galaxies has just gotten smaller, not physically smaller, but conceptually smaller for us. The space that is between the galaxies is smaller. This is because the galaxies themselves are bigger. The local group is our own cosmic neighborhood, a gravitationally bound cluster of galaxies that is dominated by three giants, the Milky Way, Andromeda, and the Triangulum galaxy. Plus, there are dozens of smaller dwarf galaxies that are orbiting around them. The total population of the group is about 80 galaxies. They are all within a 10 million light-year radius, or at least that is what we had thought before. The boundaries of the local group are in need of a redrawing. When the galaxies are bigger, their gravitational influence is extending farther. The sphere of control of each of them is growing. Territory that had seemed like neutral intergalactic space, it is actually belonging to one galaxy or another. The no man's land that is between the giants is shrinking. Andromeda is sitting 2.5 million light-years away from us. The old measurement was showing that our visible disks were separated. They were separated by 2.5 million light-years of empty space. But with the updated sizes, the picture is changing. Our dark matter halo is extending at least 250,000 light-years. Andromeda's halo is doing the very same thing. If you subtract those halos from the total distance, only 2 million light-years of truly neutral space is separating us, and it is less if the halos are extending even farther. Some models are suggesting that they might already be touching. The collision could have already begun in the invisible dark matter realm. This is changing the dynamics of the entire group. The local group is not 3 separate entities with space between them. It is 3 overlapping spheres of influence in space. The boundaries between them are becoming blurred. The territory is becoming contested between the giants. Some of the dwarf galaxies are orbiting in regions that are claimed by multiple large galaxies at the same time. Take the Magellanic Clouds, for example, for us to consider. Are they satellites of the Milky Way, or are they just passing through? The old measurements had suggested that they might be able to escape, but the new calculations are saying no to that idea. Our gravity is reaching much farther out than we had thought. The clouds are trapped, and they are permanent prisoners. In a few billion years from now, we will devour them completely. Several of the dwarf galaxies are sitting in the space between us. The space between us and the Andromeda Galaxy. Which of the galaxies do they belong to in this case? Technically, they are orbiting in the combined gravitational field. They are feeling the pulls from multiple different directions. As the Milky Way and Andromeda are approaching each other, these dwarfs are going to get caught in the middle. They will be torn apart, they will be scattered, and they will be casualties. Casualties of a great galactic war that is coming. Triangulum is facing a very similar kind of fate. It is the 3rd largest galaxy in our local group, but it is barely a giant, with only about 60 billion stars. New measurements are suggesting that it might already be falling into the Andromeda Galaxy at this very moment. The distance between them is only about 750,000 light-years. With the updated halo sizes, they are practically touching. Triangulum is not an independent galaxy after all. It is a satellite of Andromeda, or it will be very soon. Redrawing the boundaries is affecting how we are counting the galaxies. Some of the objects that we had thought were independent, they are turning out to be satellites of the larger galaxies. Others that we had thought were satellites might be independent. The total number of galaxies in the local group is staying the same, but the categorization of them is changing for us. The group's center of mass is also shifting as a result. With the larger galaxy sizes and the updated masses, the gravitational balance point of the group is moving. It is sitting somewhere between the Milky Way and Andromeda, but it is closer to Andromeda because it is slightly more massive. This point is determining how the entire group is evolving. Everything in the group is orbiting around this point. Everything is falling toward this point over time. Beyond the local group, the boundaries with the neighboring groups are also changing. The Sculptor group is sitting about 12 million light-years away. The Maffei group is closer, but it is obscured by the Milky Way's disk. These neighboring clusters are having their own gravitational zones. With the bigger galaxies, those zones are expanding. The space that is between the groups is shrinking for us. Some astronomers are now suggesting that the local group is larger than we had traditionally defined it to be, maybe 15 million light-years across instead of 10. The outer members of the group are orbiting farther out. The group is claiming more territory in the universe. More space is falling under its gravitational control. This is mattering for our understanding of cosmic structure. Galaxy groups are clustering into the superclusters. The local group is belonging to the Virgo supercluster, or possibly the larger Laniakea supercluster, depending on the definition. If the groups are larger, the superclusters are reorganizing. The hierarchy of cosmic structure is shifting at every single level. Here is the strangest part of all of this to consider. The boundaries that we are drawing are completely arbitrary. The galaxies are not respecting any imaginary lines. They are blurring together, they are overlapping, and they are merging. The concept of separate objects is a human construct. Nature is seeing continuous fields of gravity. It is seeing smooth gradients of density and no walls. There are no borders in the universe for us to see. The local group is not a collection of isolated galaxies. It is one big gravitational basin with concentrations of matter. Concentrations of matter that we are calling galaxies. You can redraw the boundaries all that you want to, but the truth is much messier than any map can show, and we are living inside of that mess right now. We are trying to chart the territory that is refusing to be charted. The star count in our galaxy has just been doubled. The Milky Way is containing approximately 400 billion stars. Every single estimate has doubled, along with the galactic size. 400 billion is a completely incomprehensible number. If you were to count one star per second, it would take you a long time. It would take you 12,700 years to count them all. That is longer than all of recorded human history, and you would still be having billions of them left. You can compare that to the population of the Earth. There are about 8 billion humans on our planet. We would be needing 50 Earths worth of people to match the number. 50 entire planets that are full of human beings. That is how many stars that we are talking about. The old estimates were saying 200 billion stars. They were wrong, and the mistake came from the sampling. Astronomers were counting the stars in very small regions, and then they were extrapolating from that small sample. They were measuring the solar neighborhood of our galaxy. They were counting the stars per light year in that area, and then they were multiplying that by the galaxy's volume. It was a simple calculation, except that the volume was wrong. If you double the radius, you are increasing the volume. You are increasing it by a factor of 8 in total. Twice as wide is meaning 8 times more space. Not all of that space is filled with stars, of course. The outer regions of the galaxy are very sparse, but even the sparse regions are contributing to the total. If you add up all of the extra volume, you are getting billions more stars. Most of these new stars are what are known as red dwarfs. They are small, dim, and they are very long-lived. These stars are making up about 70% of all stars, but they are contributing barely any of the light. You can have 1 billion red dwarfs in a region, and it still looks dark. They are hiding in plain sight from us in the galaxy. The outer halo is containing more stars than we had thought. The old surveys had missed them because they are faint and scattered, but the modern instruments, with their better sensitivity, are revealing them. Hundreds of millions of halo stars are orbiting far from the galactic disk. They are ancient stars, and they are metal-poor stars. They are the survivors from the galaxy's earliest days. Then there are all of the stars that we have devoured. Every time that the Milky Way has eaten a smaller galaxy, it has absorbed that galaxy's stars into its own population. Those stars are still existing, and they are orbiting within our halo. They are the former citizens of destroyed civilizations. They are immigrants that were forced into our galaxy by gravity. The Sagittarius dwarf galaxy alone has contributed tens of millions of stars. The stream that is wrapping around the galaxy contains about 100 million stars. Those are all new additions to the Milky Way's census. They are the former Sagittarius citizens that are now counted as ours. 400 billion stars means 400 billion chances for planets. Not every single star is having planets orbiting it, but many of them are, and maybe most of them are. Conservative estimates are suggesting that 60% of stars have at least one planet. That is 240 billion planetary systems minimum. How many of these are habitable for life as we know it? How many are orbiting in the zone where liquid water can exist? The estimates for this are varying wildly among the scientists. Conservative guesses are saying that 1% of planets are habitable. That is 2.4 billion habitable worlds in our galaxy. That number has just been doubled from the previous estimates. Even if life is incredibly rare, say 1 in a million, that is still leaving 2,400 worlds with life. 2,400 worlds in the Milky Way alone. That number has just been doubled from what we had thought before. And if intelligent life is even rarer still, say 1 in a billion, we are still having 2 or 3 civilizations out there. The Drake equation is used to calculate the number of civilizations. Every single variable in that equation has just increased. More stars means more planets, and that means more chances. The probability of finding alien intelligence has gone up significantly. It is not guaranteed, but it is much more likely now. Here is the uncomfortable question that we are now facing. If there are 400 billion stars in our galaxy, and we are only knowing a small fraction of them, what is hiding in all of the data that we have? What strange objects are lurking in the outer halo, rogue planets, failed stars, black holes, and neutron stars? Objects that we have never even imagined could exist. Every single star has its own story to tell us. A birth in a collapsing gas cloud, and a life-burning hydrogen, and an eventual death as a white dwarf or a neutron star. 400 billion stories and 400 billion lifetimes. They are all playing out right now across the galaxy. The Sun is just one of these 400 billion. It is average, it is unremarkable, and it is one voice in a choir that is so large that no one can hear the individual notes. We are not special, and we are not unique in the universe. We are just one star system among hundreds of billions, and that number has just been doubled for us. The galaxy has just gotten twice as crowded as we thought. This is making our cosmic loneliness even stranger. With so many stars, so many planets, and so many chances, where is everybody else in the vast universe? 400 billion stars, and we have not heard from any of them. Yet we have doubled the stars, doubled the planets, and doubled the chance. Doubled the chance that we are not alone in the cosmos. The bigger Milky Way is fundamentally changing the search for extraterrestrial life. You can start with the concept of the habitable zones. Each star is having a region where the planets are receiving just the right amount of heat for liquid water to be able to exist. If it is too close, the water is going to boil away. If it is too far, the water is going to freeze solid. This zone is shifting based on the star's size and its temperature. Red dwarfs are having tiny habitable zones that are close to the star. Sun-like stars are having zones that are similar to the Earth's orbit. Giant stars are having zones that are much farther out. 400 billion stars is meaning 400 billion potential habitable zones. Not all of them are hosting planets, but many of them are. The Kepler Space Telescope has discovered that planets are common. They are extremely common in our galaxy, in fact. Most of the stars are having at least one planet orbiting them. Many of them are having multiple planets in their systems. Planetary systems are the rule, not the exception. If you estimate conservatively, say that 60% of stars have planets, that is 240 billion planetary systems for us. Now you can estimate what fraction of those systems are having planets that are in the habitable zone of their star. Maybe that number is 10% of the total. That is giving us 24 billion potentially habitable planets. And that is just in our own galaxy alone, a huge number. It has just been doubled from the previous estimates. But being habitable is not meaning that it is inhabited. A planet can be having liquid water and still be sterile. It can be dead and it can be completely empty. Life is requiring more than just the presence of water. It is needing the right chemistry and the right energy sources. It is needing the right conditions over billions of years. How rare is the phenomenon of life in the universe? Nobody is knowing the answer to that question for sure. We are having just one single data point, our own planet Earth. That is it, and everything else is just speculation. Some scientists are thinking that life is inevitable given the right conditions for it to form. Others are thinking that it is vanishingly rare, a cosmic accident, a 1 in a trillion fluke of nature. Let us assume that life is moderately rare for now. Say 1 in 1,000 habitable planets is developing life. That is still 24 million living worlds in the Milky Way. That number has just been doubled from the previous estimates. 24 million planets where biology is existing, where the cells are dividing, and where evolution is operating. where the organisms are adapting and they are surviving. Most of that life is probably going to be simple. Bacteria, single cells, and some kind of slime. Intelligence is a much rarer thing to be finding. The Earth was existing for 3 billion years with only microbes. Complex multicellular life has appeared relatively recently. Intelligence has shown up just yesterday in geological time. If intelligence is 1 in a million among the living worlds, that is giving us 24 intelligent species in the galaxy. Maybe there are more and maybe there are less. The numbers are very uncertain, but doubling the galaxy size has doubled the probability. Whatever the true number is, it has just increased by a factor of 2. The Fermi paradox is getting much more intense for us. If there are so many chances for life to be existing, so many potential civilizations out there in the cosmos, where is everybody else in the vast universe? Why have we not been able to detect any signals? Why have we not seen any alien probes in our solar system? Why does the galaxy seem to be so empty for us? Some are arguing that the Great Filter is existing, a barrier that is preventing the civilizations from becoming spacefaring. Maybe it is behind us and life is just hard to start. Maybe we have just gotten very lucky on our planet. Or maybe it is ahead of us and civilizations are destroying themselves. Nuclear war, climate collapse, or artificial intelligence gone wrong. We are heading toward the filter right at this very moment. Others are suggesting that intelligence is even rarer than we are thinking. Maybe we are one of very few, or maybe we are alone. 400 billion stars and just one single civilization. Us lonely and isolated, the only voices in a silent galaxy. But here is the more hopeful perspective on this. Doubling the stars is meaning doubling the chance for contact. If there are civilizations out there, a bigger galaxy is making them more likely. More potential neighbors, more chances for signals, and more opportunities to be able to find each other. SETI, the search for extraterrestrial intelligence, has just gotten more interesting. They are scanning the sky for radio signals from alien civilizations. Every single survey is covering a fraction of the galaxy. Doubling the stars is meaning doubling the search space, but it is also meaning doubling the potential transmitters. Future telescopes are going to be searching for the biosignatures. Oxygen in the exoplanet, atmospheres, methane and ozone, chemicals that are suggesting the presence of life. The James Webb Space Telescope is already starting this work. Each new habitable planet that is discovered is one more chance for us to be able to find life. Twice as many worlds is meaning that we are probably not alone. The probability has just shifted in the favor of life. It is not a certainty and it is not a proof, but it is better odds, and better odds are meaning that there is hope for us. Somewhere in the Milky Way, orbiting one of 400 billion stars, life might be looking back at us wondering the same questions, feeling the same loneliness and hoping for contact. The galaxy has just gotten bigger, and the chances have just gotten better, and the search for life is continuing for all of us. Stand at the very edge of the Milky Way galaxy, and then look outward into the vastness of space. Where does our galaxy end and where does intergalactic space begin? The answer to that question is nowhere at all. There is no edge, just a gradual fading into the darkness. This is the uncomfortable truth of the matter for us. Galaxies are not having borders like the countries or the continents. There is no border wall, and there is no sign that is saying now, leaving the Milky Way. The stars are just thinning out very gradually over time, slowly until there are none of them left at all, or maybe just a few scattered stragglers are remaining. Where exactly does that become? Not the galaxy. This is not just a philosophical question for us. It is a very practical problem for the astronomers. Astronomers are needing a definition, a standard measurement, a way to be able to compare the different galaxies. But nature is not cooperating with this particular need. The universe is not caring about our need for clean categories. Several different definitions for this are existing, and none of them are perfect by any means at all. The optical radius is marking where the visible stars are becoming too faint to see. This is giving you the bright disk of the galaxy, the obvious part. 100,000 light-years for the Milky Way galaxy. But this is ignoring all of the faint stars in the galaxy, the dim dwarf stars and the scattered halo objects. It is like measuring a city by only counting the skyscrapers, and you are ignoring all of the houses in the suburbs. The virial radius is a much more scientific definition. It is marking where the objects are gravitationally bound to the galaxy. Inside of this radius, the stars are orbiting the center. Outside of this radius, they are drifting freely in space. For the Milky Way, this gives about 250,000 light-years. This is much better, but even this has some problems. Some of the stars that are outside of the virial radius are still moving. They are still moving with the galaxy through space. They are sharing our motion through the vast universe. They were formed here, so are they a part of the galaxy or not? The virial radius is saying no, but common sense is saying maybe. Then there is the vast dark matter halo to consider. It is extending far beyond everything else in the galaxy. If the halo is reaching 1 million light-years out, is that the real edge? Most of the astronomers are saying no to this idea. The halo is fading so gradually that choosing any boundary is arbitrary. It is like trying to mark where the Earth's atmosphere ends. Technically, it is extending for thousands of miles up, but practically it is gone after about 100 miles. Where do you draw the line for something like that? The situation is getting even worse when you consider the galactic winds. The Milky Way is producing massive outflows of gas. Supernovas are exploding and the stars are shedding their material. This gas is blowing outward into intergalactic space. It is going for hundreds of thousands of light-years out. Is that material still a part of our galaxy or not? Some of it will eventually fall back to the galaxy. The gravity is pulling it back down over time. The galaxy is recycling its gas over billions of years, but some of it is able to escape, forever lost to the void. At what point does the gas stop being Milky Way gas? And at what point does it become the intergalactic medium? The Magellanic Stream is adding another complication. The large and small Magellanic Clouds are leaking gas. They are leaking gas as they are orbiting around us. This gas is forming a long stream that is stretching across the sky. Is that stream a part of the Magellanic Clouds or the Milky Way, or is it a part of neither of them at all? All three of these answers have their own defenders. Andromeda is posing the very same problem from the other direction. Its dark matter halo might already be touching ours. When two of these halos are overlapping with each other, where does one of the galaxies end and the other begin? The space that is between them is becoming a shared territory. It is co-owned and it is disputed between the two. This is not just a matter of semantics for us. The definition is affecting the mass estimates of the galaxies. It is affecting the size comparisons that we are making. It is affecting our understanding of when the Andromeda collision truly begins. If the halos are already in the process of merging, the collision has already started millions of years ago. We are living inside of it right at this very moment. Most of the astronomers are settling on practical definitions. The disk is ending where the star formation is stopping. The halo is ending at the defined virial radius. The dark matter is extending as far as the simulations are suggesting. Each of these definitions is serving a different purpose, but none of them are perfectly capturing the reality. Here is the truth of the matter for you to consider. The Milky Way is not an object, it is a region. It is a zone of influence, a gravitational neighborhood. It has a dense core, a structured middle, and a diffuse edge. And beyond that edge, it is fading into something else. 200,000 light-years is our current best answer. But if you ask that question again in another 10 years, new measurements will have changed the number for us. They always do, as our science is always improving. The galaxy has no edge because the universe does not work that way. Everything is blending together and everything is connecting. We are living in a cosmos that is without any borders, and we are still learning how to measure it properly. The Milky Way is a cosmic cannibal, a predator. Our galaxy has grown to its current size by eating others. Hundreds of smaller galaxies have fallen into our gravitational well. They have been torn apart and then devoured by us. Their stars have now become our own stars. This is how all of the galaxies in the universe grow. It is not through a slow accumulation of material. It is through violence, galactic mergers, and cannibalism. The bigger galaxies are eating the smaller ones. The strong are dominating, and the weak are becoming meals. It is the survival of the gravitationally most massive. The evidence of these ancient meals is surrounding us. Stellar streams are wrapping all around the galaxy. Each of these streams is like a corpse, a dead galaxy, a dwarf galaxy that got too close to us in the past. The Milky Way has ripped it apart, stretching its stars. It has stretched them into long and beautiful ribbons. These ribbons are orbiting for billions of years. They are orbiting before they are dispersing completely. The Sagittarius dwarf galaxy is being eaten right now. It is an active consumption that is happening as we speak. We have caught it in the very act of being destroyed. The dwarf is containing about 400 million stars. Over the next billion years, those stars are going to scatter. They will scatter all across the vast Milky Way. In 2 billion years from now, no trace of it will remain, except for some ghosts that are in the astronomical data. But Sagittarius is just the latest victim of our galaxy. The galaxy has fed many times before this one. Gaia Enceladus was a major meal for our galaxy. About 10 billion years ago, a galaxy collided with us. A galaxy that was 1/4 of the Milky Way's mass. This was not just a minor dwarf galaxy. This was a substantial galaxy in its own right. The collision between the two was very violent. Both of the galaxies suffered, but the Milky Way won. We were able to absorb Gaia Enceladus completely. Its stars are now populating our own halo. Billions of them are former citizens of a destroyed civilization. The Gaia spacecraft was able to detect this ancient merger. It did so by studying the motions of the stars. The stars from Gaia Enceladus are orbiting differently. They are orbiting differently than the native Milky Way stars. They are moving in retrograde directions and on tilted orbit. Their motion is betraying their foreign origin to us. Chemical analysis is also confirming this for us. The Gaia Enceladus stars are having different compositions, different from the native stars of our own galaxy. They are having less of the heavy elements, and they are having different abundance patterns. They were formed in a different galaxy with a different history. Now they are orbiting here, captured and assimilated. They are now ours, a part of our own galaxy. The Kraken merger came even earlier, about 11 billion years ago. This was an even more massive collision for our galaxy. Kraken might have been half of the Milky Way's mass at that time. The merger reshaped our galaxy, and it triggered intense star formation. It built much of our current disk structure for us. The remains of Kraken are much harder to identify. This is because they are so thoroughly mixed into our galaxy. But they are there, and there are billions of them. The Sequoia dwarf the Helmi streams and Omega Centauri. Omega Centauri is a massive globular cluster that might be a core, the core of a destroyed galaxy from long ago. Each one of these was a meal, and each one was a victim. The Milky Way has cannibalized dozens, maybe hundreds of smaller galaxies over its 13 billion year history. This is how we have gotten to be so big. We started out much smaller than we are today. Maybe 10 billion years ago, the Milky Way had only 50 billion stars. It was a respectable spiral, but it was not a giant. Then we ate Kraken, and we doubled our mass. We ate Gaia Enceladus, and we grew again. We have consumed dozens of smaller dwarf galaxies. Each of these meals has added more stars to our galaxy, and each of these mergers has increased our mass. The process is continuing even today for us. The Magellanic Clouds are going to be eaten by us. Sagittarius is currently being digested by our galaxy. Small dwarfs are orbiting too close, and they are doomed. In the future, Andromeda is going to collide with us. That is going to be the final meal for our galaxy. The merger that is going to transform us completely. Galactic cannibalism is explaining why the big galaxies are growing. The rich are getting richer in the cosmic scheme of things. Once you are massive enough, your gravity is reaching farther. You are able to capture more victims in your gravitational well. You eat them, you grow larger, and your size lets you capture even more. It is a positive feedback loop, a runaway growth. The dwarf galaxies are having a very rough time. They are the prey, and they are constantly being threatened by their larger and more massive neighbors. Most of them are eventually going to get eaten. Only a few of them are able to survive in isolation. The Milky Way is dominating the local group by eating. It is eating everything that is within its reach. We have built an empire through consumption of others. But here is the strangest part of all of this. Those devoured galaxies are not gone, they are still here. Their stars are still existing, they are still shining. They are still orbiting, but they are orbiting us now. The Milky Way is not a single entity, it is a collective. It is a graveyard empire that is built from the corpses of dozens of smaller galaxies from the past. You might be made of elements that were forged in a star that once belonged to the Gaia Enceladus galaxy. Heavy elements like iron and carbon are cycling through the galaxy. Supernova remnants and stellar winds are spreading them. Eventually, those elements coalesced into our solar system. They coalesced into the Earth and into you. You are partly alien, and you are made from material that came from elsewhere, from material that came from conquered galaxies. We are all immigrants, and we are citizens of an empire that has erased its borders by eating its neighbors. The Milky Way has grown big through violence and cannibalism, and we are still eating, we are still growing, and we are still adding to our collection of stars that are stolen from others. Scientists are hating to be wrong about things, not because of their ego, but because being wrong means rebuilding. It means rebuilding everything, recalculating and rewriting papers. It means admitting to a great deal of uncertainty. The James Webb Space Telescope has forced exactly that admission. Webb was launched in December of 2021. It is a $6 billion infrared observatory. It is 100 times more powerful than the Hubble telescope. It was designed to be able to see the earliest galaxies, the first stars, and the birth of all cosmic structure. Nobody was expecting it to revolutionize our understanding of our own Milky Way galaxy. But it did, and the breakthrough came from unexpected observations. Webb is able to see through the dust better than any previous telescope. The infrared light is able to penetrate the gas and the debris that is blocking the visible light from us. This has let Webb map the regions of the Milky Way, regions that we could never clearly see before this. The galactic center, the thick dust clouds, and the far side of the disk. What Webb has found has shocked everyone in the field. More structure, more stars, and more complexity than the models predicted. The outer regions of the galaxy were not empty. They were not empty like we had thought they were. Faint stars were populating the regions that we had assumed were void. They are scattered and they are isolated, but they are there. Billions of them are out there in the vast halo. Webb has also observed the satellite galaxies with unprecedented detail. It has resolved the individual stars in the distant dwarfs. It has measured their ages, their compositions, and their distances. Each of these measurements has refined our model of the Milky Way. It has refined the model of its gravitational field. And each of these refinements has pushed the boundary outward. The critical data has come from the stellar streams. Webb has tracked these streams farther than the previous surveys. It has measured streams at enormous distances from the center, 200,000 light-years out and 250,000. These streams should not be existing if the galaxy was as small as we thought. Their very presence has proved that our estimates were wrong. But the real blow has come from the mass calculations. Webb has observed how the light from distant galaxies is being bent around the massive Milky Way galaxy itself. This is gravitational lensing, Einstein's general relativity in action. If you measure the bending, you can calculate the mass. Webb's precision has exceeded the previous instruments by orders of magnitude. The result of this work was 4 trillion solar masses. 4 trillion solar masses, or maybe even more than that. This is triple the old estimate of the galaxy's mass. The data that they have collected is undeniable now. Multiple independent methods have confirmed this new value. Scientists could be arguing with the models that they are using. They could be debating all of the different theories, but they cannot argue with the direct gravitational lensing measurements. The conferences have erupted in a great deal of debate. Some of the astronomers have defended the old measurements. Others have accepted the new data immediately. Papers have appeared that are arguing both sides of the issue. Slowly and grudgingly, the consensus has shifted. The Milky Way is bigger, much bigger than we thought. The textbooks were wrong and they are in need of a revision. Webb is continuing to refine all of these measurements. Every single new observation is adding more detail. Some of the measurements are pushing the size even larger. Others are suggesting that we are still underestimating the dark matter. The final number for the size is still climbing, but Webb has also raised some new and interesting questions. If the Milky Way is this big, other galaxies should be too. Webb has turned its gaze toward the Andromeda Galaxy, toward Triangulum, and toward distant spirals billions of light years away. In each of these cases, the galaxies have appeared larger than the previous measurements had suggested. The problem that we are having is very systematic. It is not just the Milky Way, and it is not just our local group. It is every single spiral galaxy across the entire universe. We have been measuring them all wrong for a very long time. Webb has forced the entire field to confront this uncomfortable truth. Scientists are still in the process of processing the implications. The cosmological models are in need of a revision. The galaxy evolution theories are in need of updates. The distance measurements across the universe are in need of rechecking. One single telescope and one single dataset has caused this. Cascading changes are happening through every subfield of astronomy. This is how the process of science is working. New instruments are revealing new and better data. That data is contradicting the old and outdated models. The models are then being updated or they are being replaced. Nobody is enjoying being proven to be wrong about things. But the alternative is to stay wrong forever, clinging to outdated ideas because they are comfortable, refusing to accept the evidence because it is inconvenient. Webb has given us the evidence, and it has forced the admission. It has made the scientists face the data and acknowledge their mistake. The Milky Way is not the galaxy that we had thought we knew. It is bigger, it is heavier, and it is more complex. And we are still discovering just how much bigger it is. The James Webb Space Telescope has changed everything, not through grand discoveries of the distant universe, but through humble observations of our own cosmic backyard. And in doing so, it has revealed how little we truly understood. How little we understood about our own home in the cosmos. Dark energy is the biggest mystery in all of cosmology. It is an invisible force that is pushing the universe apart. It is making the expansion of the universe accelerate. It is causing space itself to stretch out over time. Scientists have discovered it, they have measured it, and they have named it. But they do not understand what it is or how it works. And bigger galaxies have just made the mystery even worse. Here is the problem that we are now facing with this. The calculations for dark energy are depending on accurate mass measurements. You are needing to know how much matter is existing, where that matter is concentrating, and how gravity is pulling. Then you are subtracting all of the gravitational attraction. You are subtracting it from the observed expansion rate. What is remaining is the dark energy, the force that is accelerating everything. But if the galaxies are twice as large as we have measured, they must be containing much more matter than we thought. More matter is meaning that there is more gravity. And more gravity is meaning that the universe should be expanding slower, except that the expansion rate has not changed at all. We have measured that independently using distant supernovas. The universe is accelerating at a very specific rate. That part of the picture is very solid for us. So if the matter has doubled but the expansion has stayed the same, the dark energy must be different than we have calculated. It must be either stronger or it must be distributed differently. Or maybe it is not uniform all across the space. The standard model of cosmology is assuming that dark energy is constant. It is assuming it is constant everywhere in the universe, the same strength and the same properties everywhere. This is what is known as the cosmological constant, a fundamental property of space itself as far as we know. Bigger galaxies are threatening that particular assumption. If there is more matter that is pulling inward with its gravity, you are needing more dark energy that is pushing outward. You need this to get the observed acceleration rate. The ratio between the two is shifting for us. The balance between them is changing as a result. The dark energy might be much stronger than we think, or maybe our entire dark energy model is completely wrong. Alternative theories for this are existing in the field. Modified gravity and variable dark energy density, cosmic inhomogeneities, are also a possibility. Each of these theories is trying to explain why the universe behaves, why it behaves the way that it does without perfect uniformity. Bigger galaxies are giving these alternative theories more room to work. Consider the coincidence problem in cosmology. Dark energy and dark matter are contributing roughly similar amounts. They are contributing similar amounts to the universe's total energy budget. About 70% is dark energy, and about 25% is dark matter, and 5% is the normal matter that we are made of. Why are these specific ratios what they are in our universe? Why is it not 90 to 10 or 50 to 50? The similarity between the two seems to be suspicious. If you double the dark matter by making the galaxies bigger, the coincidence is becoming even worse for us. Now you are needing even more dark energy to maintain the ratio, or you are having to accept that the ratio has changed. Either way, the coincidence is in need of an explanation. Some cosmologists are suggesting that the coincidence is not a coincidence. Dark energy and dark matter might be related to each other. They could be different manifestations of the same underlying phenomenon. If the galaxies are containing more dark matter than we thought, maybe they are also producing or interacting with more dark energy locally in their own vicinity. Testing this particular idea is a very difficult thing to do. Dark energy is invisible, it is uniform, and it is unchanging, at least as far as we are able to measure it. You cannot point a telescope at it, you cannot capture it, and you cannot study it directly in any way. You can only measure its effects on the cosmic expansion. Bigger galaxies are also affecting the baryon acoustic oscillations. These are the ripples in the distribution of the galaxies. They are the frozen sound waves from the early cosmos. Cosmologists are using them as standard rulers to measure distances. You measure the spacing between the ripples and you can calculate the distances. Those distances are helping to measure the dark energy, but the ripples are depending on the galaxy clustering. How many galaxies there are, how massive they are, and how they are distributed. If the galaxies are bigger and more massive than we thought, the clustering of them is going to be changing. The ripples are going to be shifting as a result. The standard ruler is going to be getting tweaked for us. The distance measurements are in need of a recalculation, and the dark energy estimates are going to shift accordingly. The Hubble tension is also getting worse for us. This is the disagreement between the different methods. The different methods of measuring the universe's expansion rate. Local measurements that are using supernovas are giving one answer. Cosmic microwave background measurements are giving another. They are disagreeing by about 9%, a huge discrepancy. Bigger galaxies are affecting the local measurements more than the cosmic microwave background measurements. The local methods are relying on understanding the nearby galaxies. Their distances and their properties are important. If those galaxies are larger, the calibration is going to shift. The expansion rate calculation is going to change. Maybe it will be in the direction that is resolving the Hubble tension, or maybe it will not be, and the jury is still out. Here is the uncomfortable truth of this whole situation. Our cosmological model is working incredibly well for us. It is matching our observations across 13 billion years of cosmic history. But it is having some free parameters in it, dark matter and dark energy values that we are measuring, but we are not truly understanding what they are. If those measurements are wrong, the entire model is going to shake. Bigger galaxies are shaking the very foundation of the model. It is not enough to topple it, at least not yet, but it is enough to make the cosmologists very nervous. It is enough to make them question whether our understanding of dark energy, whether it is as solid as we had thought it was. The universe is accelerating, and that is a fact. But why it is accelerating and how much dark energy is driving it, that has just become much more uncertain for us. We have measured the galaxies wrong, which is meaning something. We might have measured the entire universe wrong too. Dark energy is remaining the deepest mystery in all of physics, and that mystery has just gotten even deeper for us. 200,000 light-years is the current answer. The Milky Way is measuring approximately 200,000 light-years in diameter. Maybe it is 250,000 light-years across. The exact number is depending on how you are defining the edge. But this is not the final answer to this question. It is just the best answer that we are having right now. In 10 years from now, the number is going to change. Better telescopes, better data, and a better understanding. The measurement is going to be improving over time. It always does, as our science is always progressing. Here is what we are knowing with a great deal of confidence. The galaxy is much larger than 100,000 light-years. That old number is definitely and completely wrong. We are having overwhelming evidence from multiple independent methods: stellar streams, satellite galaxies, and dark matter mapping. Every single technique is pointing to a larger size. 200,000 light-years is fitting the current data. It is matching the satellite galaxy orbits that we are seeing. It is explaining the paths of the stellar streams. It is aligning with the dark matter models that we are having. It is reasonable, it is defensible, and it is probably close to correct. But it is definitely not the final answer for us. What measurements are we still missing in all of this? Many of them are still missing from our picture. We are needing better maps of the dark matter halo. The current models are extrapolating from the inner regions. They are assuming certain density profiles for the halo, but the direct measurements of the outer halo are still sparse. Better gravitational lensing surveys would be helping us. More satellite galaxy discoveries would be refining the orbits. Improved computer simulations would be testing the theoretical predictions. We are needing deeper surveys of the faint stars. The outer halo is containing the dim red dwarf stars. They are scattered across some absolutely enormous volumes. Our current telescopes are only detecting the nearest ones. How many more of them are hiding beyond our detection limits? Are there populations of stars that we are completely missing? Future telescopes are going to be pushing the sensitivity deeper. Each of these improvements is going to be revealing more stars, and each of these discoveries is going to be extending the boundary outward. We are needing better distance measurements for these objects. Many of the stellar streams are having uncertain distances. Are they 150,000 light-years out or 200,000? The uncertainty is making the drawing of the boundaries difficult. Improved parallax measurements from Gaia are going to help. But some of the streams are orbiting so far out that parallax barely works. We are needing to develop some new techniques for this. We are needing to understand the galactic winds better. Hot gas is blowing outward from the disk of the galaxy. How far is it reaching and where is it falling back? Is that gas still a part of our own galaxy or not? The wind dynamics are affecting the mass estimates for us. They are affecting where we are drawing the line between the galaxy and the vast and empty intergalactic space between them. We are needing more satellite galaxies to be able to study. The Milky Way is having about 60 known satellites. But the simulations are predicting that there should be hundreds. Where are all of the missing satellites of our galaxy? Are they too faint for us to be able to detect them? Are they orbiting so far out that we have not surveyed that region? Every new satellite discovery is teaching us something new, something about the galaxy's vast gravitational reach. We are needing to measure the Magellanic Clouds more precisely. Are they gravitationally bound to us forever, or are they just passing through? Their orbits are depending on the Milky Way's total mass. If you measure the orbits precisely, you can refine the mass. And that is changing the size estimate of the galaxy. We are needing to understand where our galaxy is ending and where the Andromeda galaxy is beginning in space. The dark matter halos might already be touching each other. But where exactly is the boundary between the two? How do you separate two interpenetrating halos of dark matter? This is not just an academic question for the astronomers. It is determining when the Great Collision is truly beginning. The Nancy Grace Roman Space Telescope is going to help. It is launching soon and it is designed to survey huge areas. It will do so with an incredible depth of sensitivity. It will be finding the faint satellites and mapping the distant streams. It will be measuring the gravitational lensing across wide fields. Each of these datasets is going to refine our model of the Milky Way. The extremely large telescope is going to help us too. It is a ground-based giant with a mirror over 100 feet across. It will have a resolving power that is beyond anything built before. It will be observing the individual stars in the satellite galaxies. It will be measuring their velocities very precisely. Each of these measurements is going to tighten the constraints. The constraints on the galactic mass and the size. Future surveys are going to keep on improving the number. 200,000 light-years might become 220,000, or it might become 180,000 or 250,000. The uncertainty in the measurement is going to shrink, and our confidence in the number is going to increase. But the number is never going to be perfect or final. It will just be progressively better over time for us. Here is what all of this is meaning for us in practical terms. We are living in a galaxy that we are still in the process of measuring, a structure that is so large that it is defying complete observation. We are sitting inside of it, trying to map it out, and we are knowing that our view is limited and incomplete. It is biased by our very own location within the galaxy. 200,000 light-years is our best answer for today. But tomorrow is going to bring us some better instruments, better data, and some better answers to our questions. The measurement is continuing, and the galaxy is revealing itself. And we are keeping on learning just how enormous our home is. The Milky Way is bigger than we had ever thought it was. It is twice as wide, it is triple the mass, and it has 400 billion stars. It has countless planets and billions of potential homes for life. And we are only just beginning to understand its true scale. This is the galaxy that we are living in right now. It is enormous, it is complex, and it is still mysterious. It is still growing, and it is still teaching us something. Teaching us that we are knowing less than we are thinking. The final number for its size, we do not have it yet. And maybe we are never going to have it at all. But we are getting closer to it all of the time. One measurement at a time and one discovery at a time. One revelation at a time as we are moving forward. The Milky Way is 200,000 light-years wide. At least that is what we are thinking for now.